Two-envelope paradox. Imagine you're given two envelopes, each containing an unknown amount of money. One envelope has twice the amount of the other. You pick one envelope, but before you open it, you're told that there's a 50% chance the money inside is either the larger or the smaller amount. Now, you're left wondering, should you switch envelopes or keep the one you picked? It seems like the best decision is to always switch, but here's the paradox. No matter which envelope you have, switching always seems to offer a better expected value. This is the essence of the two-envelope paradox, a seemingly simple problem that challenges our understanding of expected value and rational decision-making. It's a classic example in probability theory that demonstrates how intuitive decision-making can sometimes lead us to irrational conclusions. The paradox reveals the conflicts between expected outcomes, risk-taking, and the logic of choice. Let's dive into the two-envelope paradox and explore why the decision to switch may seem so irresistible, but also leads to a logical impasse. The two-envelope paradox has its roots in probability theory and decision theory, and is closely related to problems involving expected value and rational choice. While it has been known in mathematical circles for some time, the paradox gained widespread attention after it was formally presented in probability textbooks and became a popular subject in philosophical discussions about rationality and decision-making. The paradox involves a scenario where a person is presented with two envelopes, each containing an unknown amount of money. One envelope contains twice the amount of the other, and the person must decide whether to switch envelopes after choosing one. Initially, the decision seems simple, but as the paradox reveals, no matter which envelope is chosen, the person is left with the impression that switching would always lead to a better expected outcome. This paradox highlights a contradiction in the application of expected value and rational decision-making. It challenges our intuitions about choice under uncertainty, especially when confronted with situations where outcome-based reasoning leads to conflicting conclusions. The two-envelope paradox has been widely discussed in philosophy, economics, and game theory, serving as a tool to explore the limits of probabilistic reasoning and rationality. The two-envelope paradox presents a seemingly straightforward problem that introduces a counterintuitive dilemma in decision theory and probability theory. At first glance, it might seem like a simple problem about comparing the expected values of two options. However, as we explore the logic of switching envelopes, we encounter a probabilistic conflict that raises questions about rational decision-making and the interpretation of expected value. Let's break down the paradox step by step and uncover why switching seems like the best decision, despite the fact that the expected value calculation leads to an apparent paradox. 1. The setup of the two-envelope paradox. The problem begins with the following setup. You are given two envelopes, envelope A and envelope B. One envelope contains an amount of money, say X. The other envelope contains twice the amount of the first envelope, so it contains 2X. You choose envelope A, say it contains X, but before you open it, you are given the option to switch to envelope B. The question is, should you switch envelopes or keep the one you picked? At first, this seems like a straightforward decision. You might think that if you already have X, then envelope B has a 50% chance of having 2X and a 50% chance of having X/2, so you might expect to gain by switching. But this leads us to a paradoxical reasoning process that suggests that switching envelopes always leads to a better expected value, no matter what. 2. The expected value calculation. To solve the paradox, we turn to the concept of expected value. Expected value is a measure of the average outcome of a probabilistic situation. The formula for expected value is E value equals P, outcome 1, X value 1 plus P, outcome 2, X value 2. Now let's apply this formula to the two-envelope problem. Suppose the amount of money in envelope A is X. Envelope B either contains 2X or X/2 with equal probability, since one envelope has twice the amount of the other. The expected value of envelope B is calculated as E envelope B equals 1/2x2 x plus 1/2 xx/2 equals x plus x/4 equals 5x/4. So the expected value of envelope B is 5x/4, which is greater than the amount in envelope A, which is x. This suggests that, according to the expected value calculation, switching to envelope B gives you a better outcome. 3. The paradox of always switching. Here's where the paradox emerges. If the expected value of envelope B is greater than that of envelope A, the rational choice seems to be to always switch. But the problem doesn't end here. If you switch to envelope B and then reconsider, the same reasoning applies. Now, envelope A has a 50% chance of containing 2x, and a 50% chance of containing x/2, which leads to the same expected value calculation of 5x/4. This suggests that no matter which envelope you pick initially, you should always switch to the other envelope. This creates an infinite loop of reasoning where you are always better off switching, which clearly doesn't make sense. After all, if switching is always the better choice, why would there be any distinction between the two envelopes? Both envelopes should logically have the same expected value, but the paradox shows that switching appears to always lead to a better outcome, which leads to a logical contradiction. 4. The resolution, the flaw in the reasoning. The paradox arises because the reasoning is based on a flawed interpretation of expected value. The key mistake is assuming that the expected value calculation is valid in this situation when there is no objective prior for which envelope should be favored. The two envelopes are not independent, they are part of the same probabilistic structure, and the switching decision doesn't inherently improve the situation. One way to resolve the paradox is to reframe the expected value calculation by considering the problem as a whole rather than as two independent choices. The two envelopes are tied to a single event, the random allocation of money between the envelopes. Once the initial choice is made, the expected value calculation must take into account that the two envelopes are part of the same probabilistic structure. The error comes from thinking that envelope A and envelope B are separate events with independent outcomes. In reality, the choice between the two envelopes is not independent of the initial condition, and the expected value calculation must take that into account. Thus, the paradox arises from the misapplication of the expected value formula, which fails to recognize the inherent connection between the two envelopes. 5. Reconsidering the paradox, the role of information and prior knowledge. Another way to approach the paradox is to consider the role of prior knowledge and how it affects our decision-making. The paradox seems to hinge on the idea that there is no prior information about the amount of money in the envelopes. In a typical decision-making situation, we base our choices on available information and our understanding of probabilistic outcomes. However, in the two-envelope paradox, we have no real way of knowing which envelope is more likely to contain the higher amount of money, since the choice was made randomly. In this sense, the paradox challenges our intuition about how information and probabilistic reasoning affect rational decisions. In the real world, our decisions are shaped by our ability to gather information and update our beliefs based on that information. In the case of the two-envelope paradox, however, the lack of relevant information about the envelopes makes it difficult to apply a traditional probabilistic model and arrive at a definitive conclusion. 6. Implications for decision theory and real-world applications. The two-envelope paradox has broad implications for decision theory, game theory, and rational decision-making in uncertain conditions. It highlights how expected value calculations can sometimes lead to counterintuitive conclusions when information is limited or misinterpreted. Storytelling. The paradox also touches on broader philosophical issues related to rationality and uncertainty. In situations involving uncertain outcomes and sequential decisions, the paradox shows that rational decision-making can sometimes conflict with intuitive reasoning, leading to irrational conclusions. In real-world applications, the two-envelope paradox serves as a reminder of the importance of carefully evaluating assumptions and probabilistic reasoning in situations of uncertainty. Whether in investments, insurance, or policy decisions, understanding how prior information and expectations shape our choices is crucial for making informed, rational decisions. Burali 40 paradox. Imagine you're tasked with organizing all the ordinal numbers, the numbers used to describe the order of objects in an infinite sequence. You start by creating a set that contains all of them, expecting to have an easily manageable collection. But here's the twist. As you work through your list, you realize that the set of all ordinal numbers must itself be an ordinal number. In fact, it has an ordinal that is larger than any of the ordinals it contains, leading to a contradiction. This is the essence of the Burali 40 paradox, which arises when we try to treat infinite sets in the same way as finite sets. The paradox exposes an inherent contradiction within set theory and infinity. It demonstrates that certain infinite collections cannot be treated as if they were finite, as they lead to self-referential contradiction. Let's dive into the Burali 40 paradox and explore why infinite sets of ordinals cannot exist in the same way we treat finite sets, revealing the limitations of set theory and the strange nature of infinity. The Burali-Forti paradox was first described by the Italian mathematician Cesare Burali-Forti in 1902. It arose in the context of set theory, particularly in the study of ordinal numbers. Ordinal numbers are used to represent the order of objects in a sequence, extending beyond finite numbers into the realm of infinity. Burali-Forti's paradox reveals that when attempting to construct a set of all ordinals, a contradiction arises. At the time, set theory was still being developed, and Cantor's theory of ordinals and transfinite numbers was a cornerstone of mathematical research. The paradox showed that if one attempts to construct a set of all ordinals, the result is a self-referential set, a set that contains an ordinal that is greater than any of the ordinals in the set, leading to an inherent contradiction. The Burali-Forti paradox exposed a fundamental flaw in naive set theory, the idea that any definable collection could form a set. This paradox was instrumental in the development of Zermelo-Fraenkel set theory, ZF, which introduced more rigorous rules to avoid such paradoxes. The axiomatic approach to set theory was developed in response to contradictions like the Burali-Forti paradox, and it played a pivotal role in the formalization of mathematics. The Burali-Forti paradox is a critical example in the philosophy of mathematics and the development of set theory. It highlights a fundamental issue that arises when we attempt to handle infinite sets in the same manner as finite sets, particularly when dealing with ordinal numbers, the numbers used to describe the order of elements in a sequence. At first glance, it might seem intuitive to think that the collection of all ordinals, the set of all possible orders, should itself be a valid set. However, the paradox arises when we consider the consequences of such a collection. Let's break the paradox down step by step and explore why it leads to a contradiction. 1. Understanding ordinal numbers. Ordinal numbers are numbers that describe the position of an element in an ordered sequence. For example, in the sequence 12,345, the ordinals are the natural numbers themselves, 12,345. However, ordinals are not limited to finite numbers. They extend into infinity. For example, after all the finite ordinals, there is the first infinite ordinal, denoted O plus 1, O plus 2, and so on. These ordinals continue indefinitely, forming a transfinite sequence. The key property of ordinal numbers is that they describe positions in a well-ordered set. Every set of ordinals is well-ordered by definition, meaning that every subset has a least element, and the ordinals themselves are arranged in a strict order. 2. Constructing the set of all ordinals. The Burali-Forti paradox arises from the attempt to construct a set of all ordinal numbers. Let's say we want to define a set S that contains every ordinal number. In the context of naive set theory, we would attempt to gather all of them together. S equals all ordinal. This set includes every possible ordinal, whether finite or infinite, and it should represent the collection of all ordinal numbers. At first glance, this might seem like a straightforward collection. We simply collect every ordinal into a set. However, this leads to a paradox when we try to assign a particular ordinal number to the set S. After all, S itself should be an ordinal, as it is the set of all ordinals. But what happens when we try to define an ordinal for the set? 3. The contradiction. The set of all ordinals contains an impossible ordinal. Let's walk through the contradiction in more detail. If S is the set of all ordinals, we can consider the ordinal associated with the set. Since S contains all ordinals, the ordinal corresponding to S should be greater than any ordinal that exists in the set. In other words, S should be assigned the supremum, the least upper bound of all the ordinals in S. But this creates a problem. If S contains all ordinals, then the supremum of S must be an ordinal that is greater than every ordinal in S. But how can an ordinal greater than all ordinals exist? S is supposed to be the collection of all ordinals, and yet it would need an ordinal larger than itself. This leads to a contradiction. This is the Burali-Forti paradox. The attempt to construct a set of all ordinals results in a set that contains an ordinal that cannot exist. The set S cannot be an ordinal number because it leads to a self-referential paradox. It would have to contain an ordinal greater than itself, violating the very definition of ordinals, which cannot contain an element larger than themselves. 4. The self-referential nature of the paradox. The core of the paradox is self-referential. The set S is defined as the set of all ordinals, but by definition it must contain an ordinal that is greater than any ordinal in the set. However, The set itself is not allowed to contain an ordinal larger than any ordinal it contains, because ordinals are supposed to be well-ordered and strictly defined. In more formal terms, the set of all ordinals cannot be an ordinal itself, because it violates the well-ordinal principle. The ordinals are well-ordered sets, meaning that there is a unique minimal element for every subset of ordinals. But a set of ordinals would not have a unique minimal element. It would contain an element that is larger than any of its own members, which is a contradiction. 5. The resolution Zermelo-Fraenkel's set theory. The Bootstrap Paradox pointed to a fundamental flaw in naive set theory, where any definable collection is assumed to be a set. In the case of ordinals, this assumption leads to a logical contradiction. The paradox shows that not all collections can form a set, especially when dealing with infinite collections. To resolve this paradox, mathematicians developed the Zermelo-Fraenkel set theory, ZF, which introduces more restrictive rules about how sets can be formed. Specifically, ZF set theory prohibits the formation of sets that contain all ordinals. Instead, in Zermelo-Fraenkel set theory, we have classes rather than sets that can contain all ordinals. But these classes cannot be treated as sets. This is a key distinction in modern set theory, where infinite sets are treated with more care to avoid contradictions like the Bootstrap Paradox. 6. Real-world implications and applications. The Bootstrap Paradox has important implications in fields such as set theory, mathematical logic, and philosophy of mathematics. Set theory. The paradox shows the limitations of naive set theory, emphasizing the need for formal rules to handle infinite collections, especially ordinals and other transfinite sets. It is a foundational result in the development of axiomatic set theory, which underpins modern mathematics. Mathematical logic. The paradox highlights the complexities of infinite structures and how self-referential in mathematical systems can lead to contradictions. It helps mathematicians understand the logical boundaries of formal systems. Philosophy of mathematics. The Bootstrap Paradox raises questions about the nature of infinity and how infinite sets are constructed. It challenges our intuitions about the size and structure of infinite collections and serves as a reminder of the complexities involved in modeling infinite objects. Cantor's paradox. Imagine you are given two sets. One is the set of all natural numbers, 1, 2, 3, and the other is the set of all real numbers between 0 and 1. Intuitively, you might think that both sets are infinite, but that they are equally large because they both go on forever. But here's the twist. The set of real numbers is actually larger than the set of natural numbers. This is the essence of Cantor's paradox, a paradox in set theory that challenges our understanding of infinity and cardinality. In the late 19th century, Georg Cantor demonstrated that infinite sets can be compared in terms of their sizes or cardinalities, and that some infinities are larger than others. This paradox lies in the fact that even though both the natural numbers and the real numbers are infinite, the set of real numbers has a larger cardinality than the set of natural numbers, leading to a surprising and counterintuitive conclusion about the nature of infinity. Let's explore Cantor's paradox and uncover why not all infinities are created equal. Cantor's paradox was introduced by the German mathematician Georg Cantor in the late 19th century as part of his groundbreaking work on set theory and the concept of infinity. Cantor is best known for his development of the theory of cardinality, the idea that the size of a set can be compared even if both sets are infinite. This was a revolutionary concept in mathematics at the time. Cantor's work showed that not all infinities are the same size. In particular, he proved that the set of natural numbers, n, the set of 123, is countably infinite, while the set of real numbers, r, the set of numbers between 0 and 1, for example, is uncountably infinite and has a larger cardinality. Cantor's paradox emerges from the fact that the real numbers have a greater cardinality than the natural numbers, even though both are infinite. This was counterintuitive at the time because it challenged the traditional view of infinity, which assumed that all infinite sets were of the same size. Cantor's work laid the foundation for modern set theory and has had profound implications for mathematical logic, philosophy, and the study of the infinite. Cantor's theory of cardinality led to the concept of different sizes of infinity and the continuum hypothesis, which remains a fundamental part of mathematical philosophy. The Cantor's paradox is a crucial result in the study of infinity and set theory that reveals a surprising and counterintuitive truth. There are different sizes of infinity. Cantor's work on cardinality demonstrated that not all infinite sets are equal in size, and this paradox challenges our intuitions about the nature of infinity. Let's walk through the paradox step by step and uncover why some infinities are larger than others. 1. The setup of Cantor's paradox is the concept of cardinality, the measure of the size of a set. When dealing with finite sets, comparing the size of two sets is straightforward. You simply count the elements. But what about infinite sets? Cantor's key insight was that even though two sets are infinite, they might not have the same cardinality. For example, consider the following two sets. The set of natural numbers, n equals 123, which is an infinite set of whole numbers. The set of real numbers, r, between 0 and 1, such as 0.1 1000, 230.555, which is also an infinite set. At first glance, these sets might seem like they are equally infinite, but Cantor showed that they have different sizes. The set of natural numbers is countably infinite, while the set of real numbers is uncountably infinite. The paradox arises when we attempt to compare these two types of infinity. 2. The concept of countable infinity. To understand the paradox, we first need to understand what it means for a set to be countably infinite. A set is countably infinite if its elements can be listed or enumerated in a sequence. This means that we can create a one-to-one correspondence between the elements of the set and the natural numbers. In other words, we can count the elements in the set, even if the set is infinite. The set of natural numbers n is the classic example of a countably infinite set. We can list the numbers one by one, starting with 1, 2, 3, and so on, and each number in the set corresponds to a specific position in the sequence. Cantor showed that any countably infinite set can be put into one-to-one correspondence with the natural numbers. Examples of other countably infinite sets include the set of integers z, the set of rational numbers q, and even the set of prime numbers 3. The concept of uncountable infinity. Now let's look at the set of real numbers r between 0 and 1. The set of real numbers seems infinite, just like the natural numbers, but it is uncountable, which means it cannot be listed or enumerated in a sequence. Cantor showed that the set of real numbers is more infinite than the set of natural numbers, and this is where the paradox lies. To demonstrate that the real numbers are uncountable, Cantor used a technique called diagonalization, which involves showing that it is impossible to list all the real numbers in a sequence. The key idea is that no matter how you try to list the real numbers, there will always be a real number that is not included in the list. This leads to the conclusion that the set of real numbers cannot be counted or enumerated in a sequence. Cantor's diagonalization argument. Suppose we try to list all the real numbers between 0 and 1 in a sequence. R1 equals 0, A1, A2, A3, A4. R2 equals 0, A1, A3, B4, CA4, CA4, and so on. The idea is to construct a new real number r that differs from every real number in the list by changing its digits along the diagonal. For example, take the first digit of R1, the second digit of R2, and the third digit of R3, and so on. Change each of these digits to a different number, e.g. if it's 1, change it to 2, if it's 2, change it to 3, etc. This new number r is guaranteed to differ from every real number in the list because it differs from r1 in the first digit, from r2 in the second digit, and so on. Therefore r cannot be in the list. Since we can always create a new real number r that is not in the list, we conclude that the set of real numbers is uncountable. 4. The paradox. Different sizes of infinity. The crux of Cantor's paradox is that there are different sizes of infinity. While the set of natural numbers is countably infinite, the set of real numbers is uncountably infinite, which means it has a larger cardinality. Cantor introduced the concept of cardinal numbers to describe the size of sets. The cardinality of the natural numbers is denoted 0, aleph ul, which represents the smallest form of infinity. On the other hand, the cardinality of the real numbers is denoted by c, which is strictly larger than 0. This means that the set of real numbers has a larger infinity than the set of natural numbers. This result was groundbreaking because it challenged the intuition that all infinite sets should be equally infinite. Cantor showed that infinity itself has different levels of size, and the real numbers provide an example of a larger infinity than the natural numbers. 5. Implications of the paradox has profound implications for mathematics, particularly in the study of set theory and infinity. Set theory, Cantor's work, laid the foundation for the modern understanding of infinity and set theory. It led to the development of Zermelo-Fraenkel's set theory and Cantor's hierarchy of infinities, which categorizes different types of infinite sets based on their cardinalities. Philosophy of mathematics, the paradox challenges our intuitions about the nature of infinity and how it should be understood. It reveals the strange and counterintuitive properties of infinite sets, which continue to be explored in mathematical philosophy. Mathematical logic. Cantor's work also has implications for mathematical logic, especially in the study of model theory and completeness. The paradox highlights the importance of rigorous formal systems for handling infinity. 6. Real-world applications. The concept of different sizes of infinity and cardinality is important not only in mathematics but also in other fields. Computer science. Cantor's work influences how algorithms and computational processes handle infinite sets and uncertainty. The distinction between countable and uncountable sets is essential for designing efficient algorithms. Economics and decision theory. The idea of infinite sets and uncertainty plays a role in economic modeling and decision theory, particularly when dealing with infinite sequences or continuum of choices. Galileo's paradox. Imagine you are counting the natural numbers, starting with 1, 2, 3, and so on. Now, let's introduce an infinite set of perfect squares. 1,491,625. At first, it might seem like the perfect squares are a smaller subset of the natural numbers. After all, you could simply count the natural numbers in a straightforward way, but here's the paradox. The number of perfect squares is still infinite, yet it seems like there are fewer perfect squares than natural numbers. You might think that if one set is a subset of another, the larger set must have more elements. Galileo's paradox exposes this counterintuitive result, showing that infinite sets do not always behave the way we expect. Despite the perfect squares being a smaller subset of the natural numbers, both sets are still countably infinite, and there's an equal size to both sets. Let's dive into Galileo's paradox and explore why infinite sets defy our conventional understanding of size and quantity. Galileo's paradox was first described by the Italian philosopher and mathematician Galileo Galilei in his 1638 work, Two New Sciences. The paradox arose as part of his investigations into infinity and the nature of quantities that are infinitely large. In his work, Galileo was concerned with understanding how infinite sets can be compared in terms of their size or cardinality. He observed that even though the set of perfect squares, such as 1,491,625, is a subset of the set of natural numbers, such as 12,345, both sets seem to have the same cardinality, despite the fact that the perfect squares appear to be a smaller subset of natural numbers. This led Galileo to propose the paradox. An infinite set can contain subsets that are just as large as the set itself. The paradox was a precursor to set theory and the concept of cardinality developed later by Georg Cantor. Cantor's theory of countable infinity and ordinal numbers would eventually formalize Galileo's observations. The paradox raises important questions about how we conceptualize infinity and the relationships between infinite sets, subsets, and cardinality. It also illustrates the strange and counterintuitive nature of infinite quantities, which mathematicians continue to explore in modern set theory. The Galileo's paradox challenges our intuitions about infinite sets and how their sizes relate to each other. At first glance, it seems that the set of perfect squares, such as 1,491,625, should be a
smaller subset of the natural numbers, because there are fewer perfect squares than there are natural numbers. But Galileo's paradox shows that, despite this apparent discrepancy, both sets are equally infinite. Let's break the paradox down and explore the counterintuitive reasoning behind it. 1. The setup of Galileo's paradox. The paradox is based on a seemingly simple observation. The set of natural numbers, n, consists of 12,000. 345. The set of perfect squares, 1,491,625, is a subset of the natural numbers, as each perfect square is a natural number. At first, it seems reasonable to assume that the set of perfect squares is smaller than the set of natural numbers because there are fewer perfect squares than natural numbers. In fact, if you were to count the elements in each set, you might think that the set of perfect squares is a proper subset of the natural numbers with fewer elements. But Galileo observed something surprising. Both sets are infinite. In fact, both sets have the same size in terms of their cardinality, despite the apparent difference in the number of elements. To explain this paradox, we need to think carefully about how we compare the sizes of infinite sets. 2. The concept of cardinality.
To understand Galileo's paradox, we need to define the concept of countinality. Countinality refers to the number of elements in a set. For finite sets, the countinality is just the number of elements in the set. But for infinite sets, comparing countinalities becomes more complicated. In set theory, we use the concept of countability to compare the sizes of infinite sets. A set is said to be countably infinite if its elements can be put into one-to-one correspondence with the natural numbers. This means that the elements of the set can be listed in a sequence, much like the natural numbers themselves. The set of natural numbers is the classic example of a countably infinite set. We can easily list the natural numbers as 12,345. Similarly, any set that can be listed or enumerated in this way is countably infinite. 3. One-to-one correspondence between natural numbers and perfect squares. Despite the fact that the set of perfect squares appears to be a smaller subset of the natural numbers, Cantor's diagonalization argument shows that the two sets are actually the same size in terms of cardinality. To understand this, we need to show that there is a one-to-one correspondence between the two sets. Consider the following pairing between the natural numbers and the perfect squares. 1 maps to 12 equals 1. 2 maps to 22 equals 4, 3 maps to 32 equals 9, 4 maps to 42 equals 16, 5 maps to 52 equals 25, 6 maps to 62 equals 36, and so on. In this way, each natural number is paired with a distinct perfect square. In fact, every perfect square is matched with a unique natural number, and every natural number corresponds to a distinct perfect square. This is called a one-to-one correspondence. It shows that the two sets, natural numbers and perfect squares, are equally infinite. Despite the fact that there are fewer perfect squares than natural numbers, both sets can be listed in the same way, demonstrating that they have the same cardinality. 4. The concept of different sizes of infinity, Galileo's paradox, highlights an important aspect of infinity. Not all infinite sets have the same cardinality. The sets of natural numbers and perfect squares are both countably infinite, meaning they can be placed into a one-to-one correspondence. However, this concept can be extended to sets that are uncountably infinite, such as the set of real numbers. Cantor's work, which extends the ideas that Galileo touched on, shows that there are different sizes of infinity. For example, the set of real numbers, which is uncountable, has a larger cardinality than the set of natural numbers, which is countably infinite. The paradox lies in the fact that while there are infinitely many natural numbers and perfect squares, they are both countably infinite, meaning they can be paired up in a sequence. The distinction between countably infinite sets and uncountably infinite sets is critical in set theory. For example, the set of real numbers between 0 and 1 cannot be placed in a one-to-one correspondence with the natural numbers, making it a larger infinity than the natural numbers. 5. The resolution of the paradox. The apparent paradox of Galileo's observation is resolved by the concept of cardinality in set theory. Despite the fact that the set of perfect squares is a subset of the set of natural numbers, both sets are countably infinite and therefore have the same cardinality. This paradox, along with Cantor's later work, shows that infinite sets can have different sizes or cardinalities. The paradox is a reminder that our intuitions about infinity are often flawed and that the behavior of infinite sets can be very counterintuitive. Even though we might expect the set of natural numbers to be larger than the set of perfect squares, they are actually of the same size because both are countably infinite. 6. Real-world implications and applications. The Galileo paradox has important implications for mathematics, particularly in the study of set theory and infinity. It was one of the first examples to illustrate that infinite sets can be compared in terms of their cardinality and that some infinities are larger than others. Mathematics. Galileo's paradox laid the groundwork for Cantor's work on the concept of infinity and cardinality. It helped develop the framework for understanding infinite sets and the nature of countable and uncountable infinities. Philosophy of mathematics. The paradox challenges our understanding of mathematical reality and raises questions about the nature of infinity and mathematical objects. It serves as a key example in the study of mathematical foundations and the philosophy of mathematics. Computational theory. In computer science, understanding the cardinality of infinite sets can help in the study of algorithms and computational complexity, especially when dealing with infinite loops or large data structures. Hilbert's paradox of the Grand Hotel paradox. Imagine a hotel with infinitely many rooms, all of which are occupied. The hotel is full, but then a new guest arrives and asks for a room. How can the hotel accommodate this new guest when there are no free rooms? The hotel manager, who is accustomed to working with infinite numbers, comes up with a solution. Move the guest in room 1 to room 2, the guest in room 2 to room 3, the guest in room 3 to room 4, and so on. This frees up room 1 for the new guest. This is the Hilbert's paradox of the Grand Hotel, a paradox that illustrates the strange and counterintuitive nature of infinity. Despite the hotel being fully occupied, the infinite number of rooms allows for new guests to be accommodated, demonstrating that infinite sets behave in ways that defy our usual understanding of space and quantity. Let's dive into Hilbert's paradox and explore how infinity works in the context of set theory and why this paradox challenges our intuitions about the finite and the infinite. The Hilbert's paradox of the Grand Hotel was introduced by the German mathematician David Hilbert in 1924 as part of his work on set theory and infinity. The paradox is often used to illustrate the counterintuitive properties of infinite sets, particularly in the context of countably infinite sets. Hilbert was known for his pioneering work in mathematical logic and foundational mathematics, and he used the Grand Hotel paradox to demonstrate that infinite sets do not behave in the same way as finite sets. In the paradox, Hilbert imagines a hotel with infinitely many rooms, each one occupied. Despite the hotel being fully occupied, the paradox shows that there is always a way to accommodate new guests, even when the hotel is full. The paradox challenged traditional intuitions about the nature of infinity and showed that infinite sets have properties that are fundamentally different from those of finite sets. It also served as a metaphor for understanding countably infinite sets, which have an infinite number of elements but still allow for reordering and rearranging elements in seemingly paradoxical ways. The Grand Hotel paradox remains one of the most famous illustrations of infinity in mathematics and continues to be used in discussions of set theory, cardinality, and the philosophy of mathematics. Hilbert's paradox of the Grand Hotel is a famous thought experiment that reveals some of the most counterintuitive properties of infinite sets. At first glance, the idea of a hotel with infinite rooms might seem absurd, but this paradox highlights the bizarre and paradoxical nature of infinity and challenges our everyday understanding of how space and quantity work. Let's break the paradox down, step by step, and explore how it demonstrates the strange properties of countably infinite sets. 1. The setup of the Grand Hotel paradox. The paradox begins with a hypothetical hotel, known as Hilbert's Grand Hotel, which has infinitely many rooms. Despite the hotel having an infinite number of rooms, all of them are currently occupied. This seems like a full hotel, so you might think that no more guests can be accommodated. However, the paradox shows that the hotel can still accommodate new guests, despite being full. Here's how the paradox unfolds. The hotel has infinitely many rooms, each numbered 12,345. All of the rooms are occupied by guests, so the hotel is full. A new guest arrives and asks for a room. At first, it seems impossible for the hotel to accommodate the new guest because every room is already occupied. But Hilbert, the hotel manager, knows how to handle infinity. 2. The solution. Moving the guests. The hotel manager comes up with a clever solution. Move each guest to a new room. Specifically, the manager decides to move the guest in room 1 to room 2, move the guest in room 2 to room 3, move the guest in room 3 to room 4, and so on, with each guest being moved from room N to room n+1. By doing this, room 1 is now vacant, the new guest can be accommodated in room 1, even though the hotel was originally full. This solution works because the hotel has infinitely many rooms. Since there is no last room, you can always shift guests in this manner, creating a new vacancy in room 1 for the new guest. 3. The paradox of infinite sets. The key insight of the Grand Hotel paradox lies in the fact that infinite sets have properties that are fundamentally different from those of finite sets. When dealing with finite sets, the concept of fullness makes sense. If a set has a fixed number of elements, you can run out of space. But when dealing with infinite sets, this idea breaks down. In the case of the Grand Hotel, even though the hotel is full, there is still room for more guests because of the infinite nature of the set of rooms. This is not true in finite situations. If a hotel had a finite number of rooms and they were all occupied, no more guests could be accommodated. But in an infinite hotel, no matter how many guests are already there, there's always room for more. This paradox demonstrates the counterintuitive nature of infinity. It shows that infinite sets can accommodate more elements, even when they appear to be fully occupied. It also illustrates the difference between countable and uncountable infinities. While a set of natural numbers can always be rearranged to accommodate more elements, uncountable sets, like the set of real numbers, have different properties and don't behave the same way. 4. Accommodating an infinite number of new guests. The paradox doesn't end with just one new guest. What if infinite guests arrive at the hotel, all asking for a room? Surely this would be impossible in a finite hotel. But in the Grand Hotel, the manager can accommodate infinitely many new guests by applying a different strategy. For example, the hotel manager could move the guest in room 1 to room 2, the guest in room 2 to room 4, the guest in room 3 to room 6, and so on. In this way, all even-numbered rooms are occupied. Then the manager can place the new guests in the odd-numbered rooms, room 1, room 3, room 5, and so on. This works because there are infinitely many odd-numbered rooms. The paradox demonstrates some of the strange properties of infinite sets, particularly those that are countably infinite. It lays the foundation for understanding the concepts of countability and cardinality. Mathematical logic. The paradox provides a way to visualize how infinite sets can be manipulated and reorganized. It shows that infinity behaves in ways that contradict our usual intuitions about size and quantity. Philosophy of mathematics. The paradox raises questions about the nature of infinity and how mathematicians should think about infinite quantities. It challenges the traditional finite perspective and opens up discussions about infinite processes and the limits of mathematical reasoning. Computational theory. In computer science, the idea of infinite processes or infinite sequences is important for algorithms and data structures. The Grand Hotel paradox provides insight into how infinite data structures might be manipulated, even if they seem full. Gorlam's paradox. Imagine a world where infinity and mathematical structures seem to behave differently depending on how you look at them. You might assume that a certain theory, like set theory, is universal, and that its concepts hold in every model of the world. But what if I told you that you could have a model of set theory where the real numbers, the numbers between 0 and 1, don't even exist, despite the fact that they are central to traditional mathematics? This is the essence of Scolem's paradox, a paradox that reveals the counterintuitive nature of mathematical logic and how different models of set theory can lead to dramatically different conclusions. Scolem's paradox shows that countable models of set theory can exist, even though we assume the set of real numbers is uncountable in traditional mathematics. This paradox challenges our understanding of mathematical foundations and raises deep questions about mathematical truth, abstraction, and the limits of formal systems. Let's explore Scolem's paradox and see how it reveals the surprising relationship between models, set theory, and mathematical reality. Scolem's paradox is named after the Norwegian mathematician Thoralf Skolem, who discovered the paradox in 1922 as part of his work on model theory and set theory. Skolem's work dealt with the formal foundations of mathematical logic, and his paradox emerged from the application of model theory to the axioms of set theory, particularly Zermelo-Fraenkel set theory, ZFF. Skolem's paradox is closely related to Cantor's work on the continuum hypothesis and the idea of different sizes of infinity, as well as the development of first-order logic and the concept of models. In the context of Zermelo-Fraenkel set theory, it was assumed that the set of real numbers, which is uncountably infinite, could not be represented by any countable set. However, Skolom's paradox showed that there are models of Z-set theory where the real numbers are not uncountable and infinite sets can still be countable. This revelation contradicted traditional understandings of infinity in set theory and led to a deeper investigation into the philosophy of mathematics and mathematical logic. Skolom's paradox demonstrated a key result in model theory: the relativity of mathematical truth. It illustrated that the truth of mathematical statements can vary depending on the model in which they are interpreted, leading to philosophical debates about the nature of mathematical reality and formal systems. The paradox continues to be a foundational topic in mathematical logic and the study of foundations of mathematics. Skolom's paradox is a fundamental result in mathematical logic and set theory that demonstrates how the nature of mathematical objects can vary depending on the model in which they are represented. The paradox arises from the application of model theory to set theory and exposes a counterintuitive phenomenon. Countable models of set theory can exist, even though we typically assume the real numbers form an uncountably infinite set. Let's walk through the paradox step by step to understand the surprising implications of model theory and mathematical truth. 1. The setup. The traditional understanding of set theory. In traditional set theory, the Zermelo-Fraenkel axioms, Z, provide a formal framework for dealing with sets. These axioms assume that there is a set of all sets, and sets can contain elements, such as the set of natural numbers, RR. In the set of real numbers, RR, the set of real numbers is typically assumed to be uncountable, meaning that there is no one-to-one correspondence between the natural numbers and the real numbers. In this view, we would think that the real numbers are a larger infinity than the natural numbers, and they cannot be represented by a countable set. This aligns with Cantor's work on cardinality and his proof that there are different sizes of infinity. 2. The development of model theory. The model theory of first-order logic, which deals with the structure of mathematical models, provides a formal approach to interpreting mathematical theories. A model of a theory is a structure that satisfies the axioms of the theory. In this case, a model of set theory is a set of objects, the domain, along with relations and functions that satisfy the axioms of Zermelo-Fraenkel's set theory. In model theory, there is a crucial distinction between syntax, the formal rules for constructing a theory, and semantics, the interpretation of the theory. The idea is that the theory, the syntax, is defined independently of any particular interpretation, and the model is one possible interpretation of that theory. In first-order logic, there can be many different models for the same set of axioms. These models might represent the same theory in different ways. Importantly, these models can have different properties, even though they all satisfy the same axioms. 3. The key idea of Skolom's paradox. Skolom's paradox arises when we consider a model of set theory that satisfies all the axioms of Zermelo-Fraenkel's set theory, ZF, but behaves in a counterintuitive way regarding the size of infinite sets. Specifically, the paradox shows that there exist countable models of ZF set theory, even though the theory includes the assumption that the real numbers form an uncountably infinite set. Here's the key idea. In a countable model of set theory, the set of real numbers can be represented as a countable set. This means that in some models, the real numbers are no longer uncountable. They can be treated as if they are countable, even though we know that in traditional models, the real numbers are uncountable. This result creates a paradox because it suggests that the truth of mathematical statements can depend on the model in which they are interpreted. In other words, the real numbers might be uncountable in one model of set theory, but they could be countable in another model. This contradicts the traditional understanding that the real numbers are inherently uncountable. 4. The nature of countable models. To understand the paradox, it's important to recognize that a countable model of set theory is a model where the domain, the set of all elements, is countable. This means that the elements of the model can be listed in a sequence, just like the natural numbers. In a countable model of Zermelo-Fraenkel set theory, the domain is countable, but the model still satisfies all the axioms of ZF set theory. However, because the domain is countable, there are limitations to the kinds of sets that can be represented in the model. In particular, a countable model can still satisfy the axiom that the real numbers form a set, even though, in the standard model of set theory, the real numbers are uncountable. In the countable model, the real numbers are countably infinite, and they can be listed in a sequence. which contradicts the traditional understanding that the set of real numbers is uncountable. 5. Skollem's paradox and the relativity of mathematical truth. Skollem's paradox highlights the relativity of mathematical truth, the idea that mathematical statements can be true in one model and false in another. In the case of countable models of set theory, a statement like "the real numbers are uncountable" is true in the standard model of set theory, but false in the countable model, where the real numbers are countable. This leads to the philosophical question of what it means for a mathematical statement to be true. In traditional mathematical logic, a statement is considered true if it is provable within a given formal system. However, Skollem's paradox suggests that the truth of mathematical statements may depend on the model in which they are interpreted. This has profound implications for the foundations of mathematics, as it raises the question of whether mathematical reality is absolute or whether it is relative to the model in which it is understood. 6. Implications and applications. The Skollem paradox has significant implications for mathematics, philosophy, and logic. Model theory and logic. The paradox shows how different models can yield different interpretations of the same theory. It emphasizes the importance of understanding the model-dependent nature of mathematical truth. Philosophy of mathematics. Skollem's paradox challenges the idea of an objective reality in mathematics. It raises the question of whether mathematical objects, such as the real numbers, are absolute, or whether they depend on the model in which they are represented. Set theory. The paradox has implications for how sets and infinity are understood. It shows that countable models of set theory can lead to results that are not true in the standard model, revealing the limits of traditional set theoretic approaches to infinity. Computer science and foundations of algorithms. Skollem's paradox provides insight into how formal systems and models in computer science may differ from their real-world representations, helping to refine algorithms and data structures in contexts where logical frameworks need to be adjusted for model-dependent systems. Zeno's paradoxes. Imagine you are about to race from one end of a track to the other. Before you even begin, you are told that to reach the finish line you must first reach the halfway point. Then, to reach that point you must reach the halfway point of that, and so on. The paradox is simple. If you must always cover half of the remaining distance, you will never actually reach the finish line. You will always have one more halfway point to reach. This is one of the famous Zeno's paradoxes, which challenge our understanding of motion, time, and infinity. Zeno, a philosopher from ancient Greece, proposed these paradoxes to explore the nature of infinity and the incompatibility of infinite divisions with the continuous nature of reality. In Zeno's world, motion itself seems impossible because, no matter how many steps we take, we are always left with an infinite number of smaller steps. Let's dive into Zeno's paradoxes and explore why our intuitive sense of motion and infinity can sometimes be at odds with mathematical logic. The paradoxes of Zeno of Elea, an ancient Greek philosopher, date back to the 5th century BCE and have long been a topic of discussion in philosophy, mathematics, and physics. Zeno presented these paradoxes to support the ideas of Parmenides, who argued that change and motion are illusions. According to Parmenides, reality is one unchanging whole, and the appearance of motion is a deceptive perception. Zeno's paradoxes are specifically designed to challenge the concept of infinity and illustrate that motion cannot be consistently described in a logical, mathematical way. His paradoxes primarily aim to show that if we divide an event, such as moving from one point to another, into an infinite number of smaller steps, it seems that no real progress can be made, because there are always infinitely many steps to complete. Among his most famous paradoxes are the Achilles and the tortoise paradox, the arrow paradox. These paradoxes show that infinite division of time or space creates contradictions when applied to real-world phenomena, leaving philosophers and mathematicians to struggle with the nature of continuity, motion, and infinity. In modern mathematics, Zeno's paradoxes were resolved by the development of calculus and the formal understanding of limits and infinite series, which allow us to understand how an infinite number of steps can indeed result in a finite amount of motion. Nonetheless, Zeno's paradoxes continue to provide valuable insights into the concepts of infinity and continuity, and are still discussed in philosophical and mathematical contexts today. Zeno's paradoxes present a series of thought experiments that have baffled philosophers, mathematicians, and scientists for centuries. At their core, These paradoxes challenge our understanding of motion, time, and infinity. Zeno, in his philosophical works, used paradoxes to argue against the possibility of change and motion. Despite their apparent simplicity, these paradoxes force us to confront deep questions about infinite processes and the continuous nature of reality. Let's explore Zeno's most famous paradoxes, starting with the dichotomy paradox, and see how they challenge our understanding of how things move and change. 1. The dichotomy paradox. The dichotomy paradox is the most well-known of Zeno's paradoxes. It asks us to consider the task of traveling from one point to another. Suppose you are trying to travel from point A to point B, which are a finite distance apart. To reach point B, you must first reach the halfway point between A and B. After that, you must reach the halfway point of the remaining distance, and then the halfway point of the new remaining distance, and so on, ad infinitum. The paradox arises because no matter how many steps you take, you never actually reach point B. There is always another halfway point left to reach. The infinite division of the distance seems to imply that motion is impossible, because at each point there is always an infinite number of smaller steps to complete. Understanding the paradox, infinite steps to a finite destination. At first glance, the dichotomy paradox seems to suggest that you will never reach your destination because you are always required to cover half of the remaining distance. But here's where it gets tricky. While the number of steps you need to take is infinite, the total distance you cover is actually finite. If we denote the total distance between A and B as one unit, the series of distances you travel is distance equals 1/2 plus 1/4 plus 1/8 plus 1/16 plus. This is an infinite series, but it's convergent, meaning that the sum of all these infinite terms adds up to a finite value. In fact, the sum of the infinite series is S equals n equals 1/2 n equals 1. This means that after an infinite number of steps, you actually cover the entire distance from A to B. So, even though there are infinitely many steps to take, the total distance you travel is finite, and you do eventually reach point B. This resolution of the dichotomy paradox comes from the mathematical concept of limits in calculus, which allows us to understand how infinite processes can result in finite outcomes. 2. The Achilles and the tortoise paradox. Another famous paradox Zeno posed involves the famous race between the swift Achilles and the slow tortoise. Achilles gives the tortoise a head start in the race. Zeno argues that Achilles will never pass the tortoise despite being faster. The reasoning behind this paradox is as follows. By the time Achilles reaches the point where the tortoise started, the tortoise will have moved slightly ahead. By the time Achilles reaches that new position, the tortoise will have moved again, and so on. Thus, Zeno claims that Achilles will always have to catch up to the tortoise, and so he will never overtake it. Understanding the paradox, infinite steps to a finish line. This paradox, like the dichotomy paradox, suggests that even though Achilles is faster, he cannot win the race, because there are infinitely many smaller steps for him to catch up. The key to understanding this paradox is recognizing that even infinite steps can result in a finite amount of time or distance. To resolve the paradox, we can use the same idea of infinite series and limits. Achilles is faster, so the time it takes for him to reach the tortoise's position decreases as the race continues. The total time Achilles takes to pass the tortoise is finite, even though it involves an infinite number of steps. By summing the series of time intervals Achilles takes to catch up with the tortoise, we find that the total time is finite, and Achilles will eventually pass the tortoise. The paradox highlights how infinite processes don't necessarily lead to endless outcomes, and that infinity can be contained within a finite time or space. 3. The arrow paradox. Zeno's arrow paradox presents another challenge to our understanding of motion. In this paradox, Zeno argues that an arrow in flight does not move at all. Zeno asks us to consider an arrow in flight at any given instant of time. At any given moment, the arrow is not moving to any other point, because it occupies a single location. Since the arrow is not moving at any instant, it seems that motion itself is impossible. Understanding the paradox, the illusion of motion, the arrow paradox, forces us to reconsider our perception of motion and time. At any given instant, the arrow occupies a single point, but motion is not simply a collection of instants. It is a continuous process. Just as in the dichotomy paradox and Achilles and the tortoise, Zeno's paradox relies on the misconception that time can be divided into discrete, separate moments. In modern physics and mathematics, we understand that motion is a continuous process, and the instantaneous positions of an object don't capture the full picture of its movement. The paradox is resolved by recognizing that motion can be described as a continuous change over time, and that infinite moments can be summed to produce continuous motion. 4. The philosophical and mathematical implications. Zeno's paradoxes, though resolved in modern mathematics and physics, continue to raise important questions about the nature of infinity and the continuity of time and space. They challenge us to think carefully about how we understand motion, infinity, and change in both the philosophical and mathematical sense. Mathematics. Zeno's paradoxes were foundational in the development of calculus and the understanding of limits. Calculus provides a way to describe infinite processes and show that infinite sequences or steps can result in finite outcomes, such as finite time or distance. Philosophy. The paradoxes raise deep questions about the nature of reality. If we can divide time or space infinitely, how do we reconcile this with our everyday experiences of motion? Zeno's paradoxes show that our intuition about the world often doesn't align with mathematical or physical reality. Physics. Zeno's paradoxes are also important in the study of time and motion in physics. They highlight the need for a continuous understanding of motion and time, which modern relativity and quantum mechanics have helped us refine. 5. Conclusion. Zeno's paradoxes are an enduring reminder that infinity and motion are concepts that defy simple intuition. They challenge our everyday understanding of the world and encourage deeper investigations into the nature of time, space, and infinity. The paradoxes highlight the complexity of dealing with infinite processes and the continuous nature of reality. Though modern mathematics and physics provide tools to resolve these paradoxes, they continue to serve as thought-provoking examples of the strange and counterintuitive properties of the infinite. The Benedetti's paradox. Imagine a clock that's set to tick endlessly. Each tick represents a unit of time, and you are tasked with completing a task that requires infinite steps. But here's the catch. You must complete the task by the time the clock reaches a certain point in time. The paradox arises when you realize that each task requires an infinite number of steps, yet you must complete it in finite time. The paradox becomes more mind-bending when you think about how infinity interacts with time. How can you possibly complete something infinite in a finite duration? This is the essence of Benedetti's paradox, which raises intriguing questions about the nature of infinity, time, and the completion of tasks. Despite the endless steps required to finish a task, the paradox forces us to confront the impossible. How can an infinite process conclude in a finite time frame? Let's dive into Benedetti's paradox and explore why infinite sequences and tasks don't behave the way we intuitively think they should in the real world. Benedetti's paradox was introduced by the Spanish philosopher and logician José Benedetti in the 1960s as part of his work in philosophy of time, infinity, and paradoxical reasoning. Benedetti's paradox arises from the conceptual challenges of dealing with infinite sequences and the completion of tasks within a given time frame. The paradox itself is based on the question of how infinite processes can be completed in a finite amount of time. This paradox is closely related to other famous infinite sequence paradoxes, such as Zeno's paradoxes and Hilbert's paradox of the Grand Hotel. However, Benedetti's paradox differs by focusing on the idea of completing an infinite number of steps within finite time and the logical impossibility that arises when such a task is required. Benedetti's paradox has implications for set theory, logic, and the philosophy of mathematics, particularly in how we think about infinity, time, and processes that seem paradoxical at first glance. The paradox highlights the tension between infinite sequences and temporal limitations in a way that resonates with both philosophical inquiries into the nature of time and mathematical discussions about the limits of infinity. Benedetti's paradox revolves around the interaction between infinite sequences, time, and the completion of tasks. Prosecuted. It specifically addresses the question of how we can complete an infinite process within a finite duration. The paradox challenges our intuitions about infinity and time and illustrates the difficulties in applying infinite processes to real-world problems. Let's explore the paradox step by step. 1. The setup of Benedetti's paradox. The paradox begins with the scenario of an infinite sequence of tasks that must be completed in finite time. To understand the paradox, imagine the following situation. There is a task that requires completing infinite steps. The task must be completed in a finite amount of time. The task involves performing one action per time unit, and since there are infinite steps, it seems that it would take an infinite amount of time to complete the task. Bernardetti's paradox arises when we attempt to reason about completing an infinite sequence of actions within a finite duration. Intuitively, this seems impossible. How can you complete something infinite within a finite time? And yet, the paradox implies that if the task is to be completed, the process must have an end, even though it requires an infinite number of actions. The paradox, in essence, plays with the infinite nature of tasks, our finite perception of time. If we allow that an infinite number of steps can be performed in a finite amount of time, what does that imply for the nature of infinity and time? This leads to paradoxical consequences and forces us to reconsider our understanding of processes, sequences, and limits. 2. A simple version of Benedetti's paradox, the infinite task. To make Benedetti's paradox clearer, let's consider a more simplified version of the problem. Step 1. Imagine a runner who must complete an infinite number of tasks within a finite time. Step 2. The tasks must be completed sequentially, so the runner must finish the first task before starting the second, and so on. At first glance, it seems like the runner will never finish, because there are an infinite number of tasks, and each task must be completed in finite time. If the number of tasks is infinite, it would seem that it's impossible for the runner to complete them within a finite amount of time. However, the paradox forces us to confront the possibility that the infinite tasks can be completed within a finite time, despite the impossibility of reaching the end of an infinite sequence. Exploring the paradox, time, process, and completion. The paradox becomes more perplexing when we consider that each of the tasks, though infinite in number, must still be finished by the end of the finite time. The key here is that time is finite, and infinite steps must be completed within that time. One way to think about the paradox is to imagine the following. If each task takes an infinitesimal amount of time, then it seems that completing an infinite number of tasks in finite time is theoretically possible. Each task doesn't take infinite time, it takes a finite fraction of time, but there are infinitely many tasks. Mathematically, this leads to a concept of limits. If each step takes less time than the previous one, the total amount of time spent on all the steps could converge to a finite value, even though there are infinitely many steps. This is similar to how infinite series in calculus can converge to a finite value, even though they contain infinitely many terms. However, Benedetti's paradox pushes us to confront the concept of completion in an infinite process. If the task must be completed by the end of the finite time, how can we understand this process logically? We run into the issue of infinity and completeness, which seems contradictory. 3. The implications of infinite tasks and finite time. The central issue in Benedetti's paradox is how infinite sequences interact with the finite world. We have two competing intuitions. The infinite, it seems that completing an infinite number of tasks within a finite time is impossible, because no matter how small the time for each task, there are infinitely many tasks to perform. The finite. Yet if we break the infinite tasks into smaller and smaller pieces, as is done in calculus or infinite series, it seems possible that the total time could remain finite, despite the infinite number of tasks. The paradox challenges our understanding of processes in a world where infinity exists. If we accept that infinity can be divided into smaller parts, then it seems that the tasks could indeed be completed in finite time. But the paradox reminds us that the completion of the infinite process raises a question about the concept of time itself. Can an infinite number of actions really be performed in a finite time for? Resolving the paradox, limits and infinite processes, Benedetti's paradox, can be resolved by applying the mathematical concept of limits. In calculus, we learn that infinite sequences or infinite sums can converge to finite values. Similarly, the total time required to complete an infinite number of tasks can be finite if each task takes progressively less time. This idea aligns with how infinite series work in mathematics. Although there are infinitely many terms, their sum can still result in a finite value. The resolution of the paradox lies in recognizing that while the tasks are infinite, the total amount of time spent can be finite, as long as the time per task decreases appropriately. This mathematical concept has been formalized in the theory of limits in calculus. However, the paradox remains a philosophical puzzle because it forces us to rethink the nature of time and processes. Can we reconcile the infinite with the finite in a meaningful way? Or does this conflict represent a deeper logical issue with our understanding of infinite processes? 5. Philosophical and mathematical implications. Bernard Détais's paradox has important implications for both philosophy and mathematics. Philosophy of time. The paradox challenges our understanding of time and motion. It raises the question of whether infinity can ever be fully realized in the real world. How do we conceive of infinite processes occurring in a finite time? The paradox serves as a reminder of the limits of our intuitions about the world. Mathematical logic. The paradox is important for understanding how infinite processes are handled in mathematics. It provides insight into how infinite series and limits can allow us to resolve seemingly paradoxical situations where infinite tasks or steps are completed in finite time. Formal systems. The paradox is also an exploration of how formal systems and infinite sequences can interact. It forces us to ask whether infinity can be treated the same way as finite quantities in our mathematical models. Practical applications. The ideas in Bernard Détais's paradox are relevant to fields such as computational theory and algorithmic complexity, where infinite processes are often approximated or analyzed in finite time. The paradox can shed light on the challenges of modeling infinite algorithms and understanding time complexity. Grim Reaper paradox. Imagine that there are infinitely many Grim Reapers, each tasked with killing you at a different point in time. The first Grim Reaper is scheduled to kill you at 11 o'clock p.m., the second at 10:30 p.m., the third at 10:15 p.m., and so on, with each Reaper coming at half the time interval of the previous one. If you're supposed to die at an infinite series of increasingly smaller intervals, the question arises, how can you survive this infinite sequence of deaths when death is inevitable at some point? The Grim Reaper paradox presents an intriguing paradox that explores the relationship between time, infinity, and death. If death is supposed to occur in a series of infinite steps, where each one is infinitesimally small, it seems that death is both inevitable and impossible at the same time. The paradox reveals a deep tension between our intuitions about time and the infinite. Let's delve into this paradox and explore how infinite processes can challenge our understanding of fate, death, and the continuous nature of time. The Grim Reaper paradox was introduced in 1999 by philosopher Richard Gale, and it explores the counterintuitive consequences of infinite time and the continuity of events. The paradox arises from a thought experiment in which a series of infinitely many events, in this case deaths, caused by Grim Reapers, are supposed to occur in infinitely small time intervals. Gale's paradox is a philosophical paradox that raises questions about the nature of time, infinity, and cause and effect relationships. It is a modern version of Zeno's paradoxes, such as the dichotomy paradox, where an infinite number of actions must be completed to reach a conclusion. However, in the Grim Reaper paradox, the situation is made particularly complex by the infinite division of time and the inevitability of death, which forces us to consider the paradoxical possibility that something finite, like death, could be caught in the infinite sequence of events. The paradox is particularly interesting in the context of philosophy of time and metaphysics. It challenges the assumptions that we can always predict events in a deterministic universe, especially when infinite sequences are involved. It also raises important questions about causality and the continuity of time in a world governed by the infinite. The Grim Reaper paradox is a modern philosophical problem that explores the intersection of time, infinity, and fate. At its core, the paradox illustrates the strange consequences that arise when an infinite number of events, such as death or destruction, are lined up to occur in a finite time frame. Let's break down the paradox and its implications for our understanding of time, infinity, and causality. 1. The setup of the Grim Reaper paradox. The Grim Reaper paradox is typically set up as follows. Imagine that you are to be killed by an infinite number of Grim Reapers, each assigned to strike at a specific time. The first Grim Reaper is scheduled to kill you at 11 o'clock p.m. The second Grim Reaper is scheduled to kill you at 10:30 p.m. The third Grim Reaper is scheduled to kill you at 10:15 p.m, and so on, with each subsequent Grim Reaper coming at half the time interval of the previous one. Now, let's think about this setup in terms of time. The Grim Reapers arrive at times that form an infinite sequence, with each one coming progressively closer to the present moment. The question arises, if you're set to be killed by an infinite series of Grim Reapers, how can you survive? The first Reaper is coming at 11:00 p.m., but then each successive Reaper arrives at half the previous interval of time. Can you survive this infinite process? Or will you inevitably die at some point? 2. The infinite sequence of deaths. The critical aspect of the Grim Reaper paradox is the infinite sequence of events leading up to your death. If there are infinitely many Grim Reapers, each one arriving at half the time interval of the previous one, it seems that the time before the first death shrinks closer and closer to zero. In fact, there are infinitely many Grim Reapers, each one arriving at infinitely smaller intervals. At first glance, you might assume that because there is an infinite number of events, death is inevitable. But the paradox arises when you realize that there's no final moment when death must occur. Because the time intervals keep shrinking infinitely, there never seems to be a final event, the moment when you are killed. This raises the question, how can you die at all if the infinite sequence of events never reaches an endpoint? 3. The paradoxical nature of infinite processes. The paradox becomes more puzzling when we think about how infinite processes work. If the process of dying depends on the completion of an infinite series of steps, each step taking an infinitesimally small amount of time, then it seems that the death event is both inevitable and impossible at the same time. You might think that you are stuck in a kind of infinite loop, with death always approaching but never actually occurring. This paradox is similar to other infinite sequence paradoxes, like Zeno's dichotomy paradox. In Zeno's paradox, an infinite number of steps must be completed to reach a destination, and because the number of steps is infinite, the process seems to take forever. Similarly, in the Grim Reaper paradox, there are infinitely many steps leading to death, and yet it seems impossible to reach the end of the process. 4. The paradox of causality. One way to think about the Grim Reaper paradox is in terms of causality. Each Grim Reaper is scheduled to kill you, and each Reaper's action is meant to occur at a specific time. The paradox arises because, in a traditional causal chain, there's a clear cause, death, and effect, you being killed. However, when you introduce infinite time intervals, the causal process seems to break down. Since there are infinitely many Grim Reapers, and their actions take place at progressively smaller intervals, the question becomes, can any single Reaper actually cause your death, given that all the Reapers are supposed to act in an infinite sequence, and impossible at the same time? You might think that you are stuck in a kind of infinite loop, with death always approaching but never actually occurring. This paradox is similar to other infinite sequence paradoxes, like Zeno's dichotomy paradox. In Zeno's paradox, an infinite number of steps must be completed to reach a destination, and because the number of steps is infinite, the process seems to take forever. Similarly, in the Grim Reaper paradox, there are infinitely many steps leading to death, and yet it seems impossible to reach the end of the process. 4. The paradox of causality. One way to think about the Grim Reaper paradox is in terms of causality. Each Grim Reaper is scheduled to kill you, and each Reaper's action is meant to occur at a specific time. The paradox arises because, in a traditional causal chain, there's a clear cause, death, and effect, you being killed. However, when you introduce infinite time intervals, the causal process seems to break down. Since there are infinitely many Grim Reapers, and their actions take place at progressively smaller intervals, the question becomes, can any single Reaper actually cause your death, given that all the Reapers are supposed to act in an infinite sequence? Can causality still apply when there are infinite causal steps? This leads to the problem of how infinite processes interact with the logical structure of causality. We tend to think of causal processes as finite, where one event leads to another in a clear, finite sequence. The Grim Reaper paradox exposes the difficulty in applying causality to infinite scenarios. 5. The resolution. Understanding infinite time and infinite sequences. There are a few ways to resolve the paradox, though each approach requires us to reconsider our assumptions about infinity and time. One way to resolve the paradox is by recognizing that infinite sequences can still result in finite outcomes. as is demonstrated by calculus and the theory of limits. In the case of the Grim Reaper paradox, the time intervals between the arrival of each Grim Reaper shrink infinitely, but they still add up to a finite amount of time. This is because the sum of the infinite sequence of time intervals is actually a convergent series. Mathematically, the sum of the times is t equals 1/2 plus 1/4 plus 1/8 plus 1/16 plus. This is a geometric series, and its sum is s equals 1. Thus, even though there are infinitely many Grim Reapers, they are all scheduled to arrive within a finite amount of time, namely 1 unit of time. As a result, the paradox is resolved by recognizing that the process of dying can indeed be completed within a finite duration. However, this conclusion raises further questions about how infinite processes work in the real world, especially when dealing with infinite sequences and causality. While we can resolve the paradox mathematically, the philosophical implications of infinite sequences are far from simple. 6. Philosophical and mathematical implications. The Grim Reaper paradox has profound implications for both mathematics and philosophy of time and causality. The paradox forces us to reconsider how we think about infinity and its relationship to causality. How can infinite steps lead to a finite result? What does this say about the nature of time and causality in the real world? Mathematical logic. The paradox highlights the role of infinite sequences and convergent series in mathematics. It challenges our intuitions about the infinite and finite and shows that infinite processes can indeed result in finite outcomes. Modern physics. In modern physics, the Grim Reaper paradox is relevant to discussions about infinite time and the structure of the universe. How do we understand infinite time and space in the context of the cosmos and quantum mechanics? Existential questions. The paradox also raises important existential questions about death, time, and fate. If death is the result of an infinite process, how do we conceptualize our mortality in a world where time and infinity are so deeply connected? Randi's series paradox. Imagine you have an infinite series of numbers where each number alternates between 1 and 1. 1 plus 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 1. At first glance, the sum seems to oscillate between 1 and 0, leaving you with no clear answer. Grandi's series paradox presents this strange and counterintuitive series, showing how infinite sums can lead to paradoxical results. The series, often written as s equals 1, 1 plus 1, 1 plus 1, plus 1 plus 1 plus 1 plus 1, plus 1, plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, is at the heart of the paradox. If we try to sum the series using conventional methods, the result seems to flip between 1 and 0. But what if there's a way to make sense of this paradox? Can we assign a finite value to an infinite series that doesn't seem to settle on a particular sum? Randi's series challenges our understanding of infinite series and summation. Let's explore the paradox and see how infinity interacts with our expectations about summation and finite results. Grandi's series paradox is named after the Italian mathematician Girolamo Grandi, who introduced the series in the 17th century. The series, written as 1 plus 1 plus 1 plus 1 1 plus 1 1 plus 1 1 plus, appeared in Grandi's work on infinite series and summation methods. Grandi's work was part of the early exploration of infinite series and their properties, long before the formal development of calculus and summation techniques. Grandi's series is a divergent series, meaning that it does not converge to a single value in the usual sense. However, the paradox arises when we attempt to assign a value to the series, despite its lack of convergence. The series oscillates between 1 and 0, and this behavior presents a logical problem. How can we make sense of this infinite process and assign a finite sum to it? The paradox prompted mathematicians and philosophers to explore the foundations of infinite summation, leading to the development of techniques for handling such series, including Cesaro summation and regularization methods. Grandi's series is now used as a teaching tool in both mathematics and philosophy to illustrate the complexities of infinite sums, convergence, and the limits of conventional reasoning when dealing with infinity. Grandi's series paradox is an important problem in the study of infinite series, summation techniques, and mathematical logic. It presents a paradox where an infinite sequence of numbers leads to a seemingly contradictory result. the series doesn't converge in the usual sense, but can still be assigned a value through specialized methods. Let's walk through the paradox step by step and explore the mathematical concepts that help resolve it. 1. The setup. Grandi's series. Grandi's series is defined as S equals 1 plus 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 S. At first glance, it's clear that this series alternates between adding 1 and subtracting 1. The sequence does not settle on a single number. If we try to compute the sum, we notice the following. After the first term, S1 equals 1. After the second term, S2 equals 1. 1 equals 0. After the third term, S3 equals 1. 1 plus 1 equals 1. After the fourth term, S4 equals 1 plus 1 plus 1 plus 1 equals 0. The sum oscillates between 1 and 0, without approaching any fixed value. This presents a paradox, as we expect a series of numbers to either converge to a finite value or diverge in a well-defined manner, but this series seems to do neither. 2. The traditional approach, divergence. In classical analysis, a series is said to converge if the partial sums, the sums of the first n terms, approach a single value as n increases. For Grandi's series, however, the partial sums alternate between 1 and 0, and no matter how far you go, you can never settle on a specific value. Snail equals 1, 0, 1, 0, 1. This suggests that the series diverges, since it doesn't settle at a single value. But this conclusion leaves us with a paradox. How do we handle divergent series that seem to approach multiple values, but don't clearly settle on one? 3. Cesaro's summation, a new approach to summing Grandi's series. To resolve the paradox, mathematicians developed alternative methods of summation. One such method is Cesaro's summation, which provides a way to assign a finite value to certain divergent series by considering the average of the partial sums. The Cesaro sum of a series is computed by taking the average of the first n partial sums as n approaches infinity. In the case of Grandi's series, we calculate the partial sums as follows. S1 equals 1, S2 equals 0, S3 equals 1, S4 equals 0, S5 equals 1, S6 equals 0. Now, we compute the average of these partial sums. Average of first one term equals S1/1 equals 1. Average of first two terms equals S1 plus S2/2 equals 1 plus 0 plus 2 equals 0.5. Average of first three terms equals S1 plus S2 plus S3/3 equals 1 plus 0 plus 1 plus 3 equals 0.666. Average of first four terms equals S1 plus 1 plus 0 plus 4 plus 4 plus 4 plus 4.5. As we continue this process, the average of the partial sum starts to approach 0.5 as n increases. In the limit, the Cesaro sum of Grandi's series is Cesaro sum equals 0.5. This means that by using Cesaro summation, we assign the value 0.5 to Grandi's series, despite the fact that the traditional sum of the series does not converge. 4. Regularization and other methods. In addition to Cesaro summation, there are other techniques for assigning values to divergent series, such as Abel summation and Borel summation. These methods provide alternative ways to sum series that do not converge in the traditional sense. For example, Abel summation involves considering the power series of a function that generates the terms of the series. By analyzing the analytic continuation of the generating function, it is possible to assign a value to Grandi's series using complex analysis. These methods have been formalized and developed as part of the study of regularization, which is the process of assigning finite values to divergent series. In physics, such techniques are often used to handle infinite quantities in quantum mechanics and renormalization. 5. Philosophical and mathematical implications. Grandi's series, paradox, forces us to confront some fundamental questions about the nature of infinity and the convergence of series. While we usually think of the sum of an infinite series as either converging to a fixed value or diverging to infinity, Grandi's series demonstrates that some infinite series can be assigned a finite value despite not converging in the traditional sense. Philosophy of infinity, the paradox, raises questions about how we should understand infinity in a mathematical context. Is it possible for infinite processes to have finite results? What does it mean to sum an infinite number of terms? And how do we reconcile this with our intuitions about the finite world? Mathematical logic. The paradox challenges the classical understanding of convergence and summation in analysis. It highlights the importance of alternative summation methods like Cesaro's summation and their role in extending the concept of summation to divergent series physics. In modern quantum field theory and renormalization, Grandi's series and other divergent series are encountered in the regularization of infinite sums, where infinity is handled mathematically to produce finite, meaningful results. This paradox is relevant to how infinite quantities are treated in the real world. Ross-Littlewood paradox. Imagine that you're sitting at a table with a friend and you're told that you have a 1 in 10 chance of winning a prize. But here's the twist. You are going to roll a die and you have to keep rolling it until you finally get a 6. The catch? There are infinite dice rolls allowed and you are promised to win eventually. The paradox arises when you try to reconcile the idea that you are guaranteed to win over an infinite sequence of rolls, yet at every moment the odds of winning seem to be just 1 in 10. How can the odds of winning remain the same, yet you are guaranteed success in infinite time? This is the essence of the Ross-Littlewood paradox, which explores the counterintuitive relationship between probability and infinity. The paradox challenges our understanding of causality, infinite processes, and the idea of eventual success. Let's dive into the Ross-Littlewood paradox and see how infinite events and probability theory lead to a paradoxical conclusion about inevitability and chance. The Ross-Littlewood paradox is named after two mathematicians, Philip J. Ross and John Littlewood, who introduced it in the 20th century. The paradox highlights a striking result in probability theory and the nature of infinite processes. In its simplest form, the paradox involves the concept of infinite events and guaranteed outcomes, such as winning a prize after an infinite number of tries. The paradox arose from a thought experiment designed to challenge conventional notions of probability and causality. In this thought experiment, one is promised that success will eventually occur, yet the probability of success in each individual attempt seems infinitesimally small. The paradox exposes a disconnect between the infinite nature of the process and the finite probability associated with each individual event. Mathematically, the paradox is related to discussions in probability theory about infinite sequences of events, eventual certainty, and how these concepts can seem to contradict the idea of independent events. The Ross-Littlewood paradox serves as a useful tool in probability theory and philosophy of mathematics, helping us explore the limits of infinite processes and the nature of probability when applied to real-world scenarios involving infinite sequences. The Ross-Littlewood paradox presents an interesting problem in probability theory that highlights the strange and counterintuitive consequences of infinite events. It raises the question, can we reconcile the infinite nature of events with the probability of eventual success? Let's explore the paradox and break it down step by step, looking at how infinite processes and probability theory interact in a seemingly paradoxical way. 1. The setup of the Ross-Littlewood paradox. The paradox starts with a simple setup involving an event with a probability of 1 in 10 of happening at each trial. You're sitting at a table and you roll a die. The goal is to roll a 6. You continue rolling the die until you roll a 6 and you are guaranteed to win eventually, after enough rolls. At first, the probability of rolling a 6 on any single roll is 1 in 10. This means that the odds of not rolling a 6 on any given roll are 9 in 10. So for each individual roll there's a small chance of winning, but since you're promised that you'll eventually win, the paradox lies in how infinite rolls seem to guarantee an eventual win even when the odds of success per roll remain low. The paradox challenges our understanding of infinite processes and the idea of eventual certainty. How can we reconcile the fact that each roll has a low chance of success, yet you are guaranteed to win after infinite rolls? Intuitively, this seems contradictory. 2. Probability and infinite events. To understand the paradox, we need to think about how infinite sequences of events work in probability. In the case of infinite dice rolls, we are dealing with a sequence of independent events where the probability of success on each roll is constant, in this case 1 in 10. However, the process involves infinitely many chances, and this is where the paradox arises. Let's calculate the probability of never rolling a 6 after an infinite number of rolls. The probability of not rolling a 6 on any single roll is 1/10 equals 9/10. So the probability of not rolling a 6 after n rolls is n approaches infinity. The probability of never rolling a 6, i.e. the probability of failing to win, approaches 0. Limit 0 approaches 0, 0, 0, 0. This means that as you continue rolling the die infinitely, the probability of never rolling a 6 becomes infinitesimally small. In fact, it approaches 0 as the number of rolls increases without bound. Therefore, the probability of eventually rolling a 6 after infinitely many rolls is 1, 0 equals 1. This suggests that infinite rolls lead to inevitable success. Despite the fact that the probability of success on each individual roll is only 1 in 10, the infinite number of trials ensures that success will occur. The paradox arises because probability tells us that each roll has a low chance of success, but the infinite number of trials forces success to happen eventually. 3. The paradox of eventual success. The core paradox of the Ross-Littlewood problem lies in the apparent contradiction between the low probability of success on each individual trial and the guaranteed success after infinitely many trials. How can something that seems unlikely at each step, 1 in 10, become certain in the infinite limit? In practical terms, this paradox seems impossible. If you roll a die once, the probability of success is 1 in 10, which seems quite small. If you roll it a second time, the odds of success for the second roll are still 1 in 10. The idea that after an infinite number of rolls you are guaranteed to win seems to defy our understanding of probability. However, the paradox illustrates a key feature of infinite processes. Infinite sequences of independent events can lead to certain outcomes, even when the probability of success for each individual event is small. The infinite nature of the process makes success inevitable, because infinite trials give an infinite number of chances. 4. Resolving the paradox, the nature of infinite sequences. The resolution of the Ross-Littlewood paradox lies in understanding how infinite processes interact with probability theory. The paradox demonstrates that while each individual event in an infinite sequence might have a small probability of success, this phenomenon is similar to the way infinite series work in mathematics, particularly convergent series. In this case, the probability of failure over n trials is infinitesimally small as n grows. The process of infinite events is a form of limit, where the probability of success approaches 1 as the number of events increases. The paradox shows that infinite sequences are not just a theoretical curiosity, but have real consequences for understanding eventual certainty. The infinite number of trials ensures that the event will eventually occur, even though each individual trial seems unlikely. 5. Philosophical and mathematical implications. The Ross-Littlewood paradox raises important philosophical and mathematical questions about probability, infinity, and causality. Probability theory, the paradox challenges our intuitions about infinite events. It forces us to reconsider how infinite processes behave and how they lead to certain outcomes. It also illustrates how infinite sequences of low probability events can lead to inevitable success. Philosophy of time and causality. The paradox also raises deep questions about the nature of time and causality. If events can occur infinitely, how do we understand the concept of causality in a world with infinite sequences? Does infinite time require us to rethink our notions of probability and eventuality? Infinity and the real world, the paradox, highlights the difficulty of applying the concept of infinity to the real world. While infinite sequences can be resolved mathematically, they seem counterintuitive when applied to practical situations, such as the process of rolling dice or making decisions in an infinite time frame. Philosophy of mathematics. Finally, the paradox touches on the philosophy of mathematics and the concept of truth in mathematical models. Can infinite processes provide meaningful insight into the nature of reality, or are they simply a theoretical construct? Thomson's lamp paradox. Imagine a lamp that can be switched on and off at will, but here's the catch. Every time the lamp is switched, the time intervals for switching it are halved. First, you switch the lamp off after 1 minute, then after 1/2 minute, then after 1/4 minute, and so on, halving the time each time. So how long will it take to switch the lamp off? At first it seems like you'll never turn the lamp off, because there are infinitely many steps, but the paradox deepens. After an infinite number of switches, where does the lamp actually end up? Is it on or off? The Thomson's lamp paradox forces us to confront the contradictions that arise when infinite actions and continuous time are involved. Can you complete an infinite number of actions in finite time? And how do you assign a definite state, on or off, when an infinite process is involved. Let's explore this paradox and see how infinite sequences and causality challenge our understanding of action and time. Thomson's lamp paradox was introduced by the philosopher J.J. Thomson in 1954 as a thought experiment in the philosophy of time and infinity. Thomson used the paradox to illustrate problems of infinite processes and the continuity of time. In this paradox, a lamp is repeatedly switched on and off at halving time intervals, so, after an infinite number of actions, it's unclear whether the lamp is on or off. The paradox raises questions about the nature of infinite actions, converging time sequences, and how we interpret completion in infinite processes. It's also a challenge to our understanding of time and causality, showing that infinite actions in a finite amount of time can create contradictions when it comes to determining final states or outcomes. Thomson's lamp paradox touches on ideas from philosophical logic, set theory, and mathematical analysis, especially when we consider infinite sequences and limits. It highlights the limitations of applying finite reasoning to infinite processes and raises important questions about action and causality in the context of continuously occurring events. Though mathematically resolvable with concepts like limits and convergence, the paradox remains a philosophical puzzle that continues to stimulate discussions about the nature of time and action in infinite contexts. The Thomson's lamp paradox presents a fascinating challenge for both mathematical analysis and philosophy of time. At its core, the paradox explores the infinite nature of time and actions and raises questions about the final state of an event that is continually interrupted by new actions. The paradox forces us to confront infinity, time, and causality in a way that seems contradictory to our normal understanding. Let's break down the paradox and explore how it demonstrates the problems of infinite sequences in finite time. 1. The setup of Thomson's lamp paradox. The setup of the Thomson's lamp paradox is as follows. A lamp is initially on. Every minute the lamp is toggled, switched off if it is on or on if it is off. The time intervals for toggling the lamp are halved at each step. First, after 1 minute, toggle the lamp. Then, after 1/2 minute, toggle the lamp again. After 1/4 minute, toggle the lamp once more. Continue this process indefinitely, halving the time for each successive action. The central question of the paradox is, what is the state of the lamp after an infinite number of switches? The lamp will have been toggled an infinite number of times, but because each toggle happens after infinitely smaller time intervals, the question arises, can an infinite process ever truly reach completion? 2. The infinite process of toggling. The paradox becomes interesting because of the infinite number of steps involved in switching the lamp. If each toggle happens after a time interval that is halved each time, the process of toggling appears to never end. In other words, you are making an infinite number of switches in a finite amount of time, because the total time to complete all the actions adds up to a finite value. The total time t taken to complete all toggles is the sum of the infinite series of time intervals, t equals 1 + 1 / 2 + 1 / 4 + 1 / 8 plus. This is a geometric series, and the sum of this infinite series is t equals 1 / 1 / 2 equals 2, so the total time for the entire infinite process is 2 minutes, even though there are infinitely many toggles. This seems like a paradox. We're completing an infinite number of actions in just 2 minutes. But the real paradox lies in what happens to the lamp after the infinite sequence of switches. 3. What happens at the end of infinite time? Now, the key part of the paradox. After completing all the actions in the finite time of 2 minutes, what is the final state of the lamp? Intuitively, you might think that since each toggle happens at smaller and smaller intervals of time, and the toggling alternates between on and off, the lamp will end up in a specific state. However, because there are infinitely many toggles, determining whether the lamp is on or off becomes ambiguous. At any point in the process, there is still an infinite number of remaining toggles, each with a half-sized time interval. So the process seems never-ending and incomplete, even though we have performed an infinite number of actions within a finite time. This creates a contradiction. If we've performed infinitely many actions, how can the lamp have a definite final state? The paradox raises the question, can infinite actions be completed in finite time, and can they lead to a final outcome? 4. Resolving the paradox with limits mathematically. The paradox can be approached by considering the concept of limits and the completion of infinite sequences. The time intervals for each toggle decrease as tn equals 1, 1/2, 1/4, 1/8. The sum of these times is finite, as shown earlier. However, the final state of the lamp after the infinite sequence of toggles depends on whether we think of the toggles as occurring at a single moment in time or over infinitely many moments. In mathematical terms, the state of the lamp after infinite toggles can be seen as the limit of the alternating sequence. On and off states. The alternating sequence of 1, 1, 1, 1, 1, 1, 1, it does not converge to a single value, it oscillates between 1 and 1. Therefore, the state of the lamp after infinitely many toggles is undefined in the usual sense. 5. The philosophical implications of infinite time, Thomson's lamp paradox, forces us to reconsider our intuitions about time, infinity, and causality. It illustrates the strange consequences of applying infinite processes to finite time intervals, time and completion. The paradox shows that infinite processes can be completed within finite time, but determining the final state of the process becomes ambiguous. This challenges our understanding of how time and infinity interact, and how action can be understood when it spans infinite intervals. Causality. Thomson's lamp also highlights issues with causality. If an infinite number of actions are performed, how do we define the cause of the final state? Is there a single cause that leads to the final state, or do the infinite actions create a state of perpetual uncertainty? Philosophy of infinity. The paradox raises questions about the nature of infinity. Can infinity be resolved or understood in finite terms, or does it always create paradoxes that our finite logic cannot handle? 6. Real-world implications. Although Thomson's lamp paradox is a philosophical and mathematical problem, it has interesting implications in the real world. Quantum mechanics. The paradox is somewhat analogous to the quantum mechanics paradoxes, where quantum states can exist in superposition, multiple states at once, until they are observed. Similarly, the lamp state is in a kind of superposition of on and off until the process is measured. Computational theory. In algorithm design and computational theory, dealing with infinite loops or infinite series of operations within finite time is crucial. This paradox helps illustrate how infinite processes can be conceptually managed in computational models, even if they cannot be fully resolved. Banach-Tarski paradox. Imagine you have a solid ball in three-dimensional space, and you are tasked with dividing it into a finite number of pieces. At first, it might seem like dividing it into a few pieces would give you smaller sections of the original ball, but here's the twist. You can divide the ball into a finite number of pieces, and using perfect precision, reassemble those pieces to create two identical balls, both the size of the original. The Banach-Tarski paradox is a startling consequence of infinite set theory and measure theory, revealing that infinite processes can yield seemingly impossible results in geometry. The paradox challenges our understanding of volume, space, and geometry, showing that infinite divisions can lead to results that defy our physical intuition. How can you divide a ball into pieces and get two identical ones? Let's explore the Banach-Tarski paradox, uncovering the surprising implications of infinity and mathematics in three-dimensional space. The Banach-Tarski paradox was introduced by Polish mathematicians Stefan Banach and Alfred Tarski in 1924 as part of their work in set theory and geometry. The paradox arose from the application of infinite sets and group theory to geometric objects, particularly spheres, in three-dimensional space. Banach and Tarski's work built on measure theory and the concepts of infinity and mathematical operations that were being explored at the time. The paradox shows that it is possible to partition a solid object, such as a sphere, into a finite number of pieces, and then reassemble them into two identical copies of the original object, without any stretching, shrinking, or distortion. This result is based on the axiom of choice, a controversial principle in set theory that allows for the selection of elements from an infinite set in ways that defy traditional geometric intuition. Although the Banach-Tarski paradox is mathematically rigorous, it has counterintuitive consequences for our physical understanding of objects in space. It highlights the strange and often counterproductive properties of infinite sets, partitions, and rearrangements in geometry. The paradox has sparked much discussion in the philosophy of mathematics and foundational set theory, raising questions about the nature of infinity and how it interacts with the real world. The Banach-Tarski paradox is one of the most famous and bizarre paradoxes in mathematics, as it shows how infinite sets can behave in ways that are deeply at odds with our physical intuitions. It provides a mathematical framework for dividing a solid object, such as a sphere, into a finite number of pieces and then reassembling them into two identical copies of the original object. Let's break down this paradox and explore its surprising implications for infinity, geometry, and set theory. 1. The setup of the Banach-Tarski paradox. The paradox begins with a simple but incredibly strange statement. You start with a solid sphere, say a ball. Divide the sphere into a finite number of pieces. Reassemble these pieces to form two identical spheres, each the same size as the original sphere. At first glance, this sounds impossible. How can you take a finite number of pieces and somehow duplicate the original object? Surely, splitting an object and reassembling it should result in the same number of objects, not two identical objects. However, Banach and Tarski's construction proves that under the axiom of choice, a foundational principle in set theory, this scenario is mathematically valid. The key to the paradox is the use of infinite sets and the mathematical operations that are possible when dealing with these sets. 2. The role of the axiom of choice. The axiom of choice is a controversial and powerful principle in set theory, which states that given any collection of non-empty sets, there exists a way to select one element from each set. While this principle is useful in many areas of mathematics, it can lead to counterintuitive results when applied to infinite sets. In the Banach-Tarski paradox, the axiom of choice is used to select elements from the sphere in such a way that the resulting pieces do not have a clear geometric interpretation. These pieces are not simply geometrically congruent in the traditional sense, i.e. they don't correspond to regular shapes like cubes or smaller spheres. Instead, the pieces are constructed using sets of points that are mathematically defined but geometrically unrecognizable. This is a critical point. The pieces that make up the two new spheres are non-measurable sets. This means that the pieces do not have a well-defined volume or shape in the usual sense of geometry. They exist only in the context of mathematical abstraction. The paradox doesn't work in the physical world as we understand it, but it is mathematically valid in a purely theoretical sense. 3. The mathematical construction of the paradox. To understand how the Banach-Tarski paradox works, we need to examine the mathematical construction behind it. The process involves a group action on the sphere, where we apply rotations and translations in three-dimensional space. Step 1. Divide the sphere into pieces. The sphere is divided into a finite number of pieces, and these pieces are constructed in such a way that they cannot be described using traditional geometric methods. These pieces are often referred to as non-measurable sets, and their exact shape and size can't be understood in a conventional way. The construction of these sets relies on the axiom of choice. Step 2. Apply group actions. The pieces are then rearranged using rotations and translations. These transformations are applied to the pieces in a way that preserves the structure of the sphere, but the individual pieces are not identical to any original segment of they are moved around and reassembled into a new configuration. Step 3. Reassemble into two identical spheres. After the pieces have been rearranged using group actions, the result is two spheres, each the same size as the original sphere. This step is where the paradox occurs. Despite the fact that the sphere has been divided into a finite number of pieces, and those pieces have been moved around, you end up with two identical spheres. This happens because the infinite precision of the group actions, coupled with the fact that the pieces are non-measurable, allows for a reorganization that leads to two identical copies of the original sphere. 4. The nature of non-measurable sets. Of the most puzzling aspects of the Banach-Tarski paradox is the role of non-measurable sets in the construction. A non-measurable set is a set of points that cannot be assigned a volume in the usual sense of geometry. This concept is counterintuitive because, in our everyday experience, we think of objects having a definite size or volume. However, in the context of set theory, there are certain sets that cannot be assigned a traditional volume because they lack structure. The pieces in the Banach-Tarski construction are non-measurable, meaning they don't have a conventional volume. This lack of volume is what allows the infinite number of pieces to be rearranged into two identical objects, as we can't meaningfully measure their individual sizes in the traditional sense. 5. The paradoxical nature of the result. The Banach-Tarski paradox reveals an important mathematical insight. Infinite sets can behave in counterintuitive ways that defy our physical intuition. In the real world, we understand that dividing an object into smaller pieces and then reassembling them should not lead to a larger object. But in the world of set theory and infinite sets, the rules are different. The paradox challenges our notions of geometry and measure. It forces us to rethink what it means to divide and reassemble an object, especially when dealing with infinite precision and abstract mathematical sets. 6. Philosophical and mathematical implications. The Banach-Tarski paradox has profound implications for both mathematics and the philosophy of mathematics, infinity and paradox. The paradox challenges our intuitions about infinity and the real world. In the physical world, dividing an object and reassembling it cannot create more than the original object, but in set theory, the infinite nature of the pieces allows for a doubling of the object. Mathematical logic and set theory, the paradox is rooted in set theory and measure theory, which are foundational fields in mathematics. It raises questions about how infinite sets behave and how they can be manipulated in ways that seem impossible in the physical world. Philosophy of mathematics. The paradox also touches on philosophical questions about the nature of mathematical objects. Are mathematical objects like spheres and points real, or are they merely abstract constructions? Can we ever apply infinite processes in the real world, or are they purely theoretical? Physics and the real world. In the real world, objects have a definite volume, and the Banach-Tarski paradox cannot be physically realized. It serves as a reminder that mathematical abstraction can lead to results that do not correspond to physical reality, particularly when dealing with infinite sets. Coastline paradox. Imagine trying to measure the length of a coastline, like the jagged coastlines of a country or an island. You might think that measuring the length is simple, just follow the shoreline with a ruler or a tape measure. But what if I told you that as you measure with finer and finer scales, the length of the coastline seems to increase without bound? The coastline paradox is a surprising and counterintuitive result that arises when we attempt to measure natural objects, like coastlines, with increasing precision. The paradox shows that the length of irregular objects can become infinite as we measure them at smaller and smaller scales. As we use finer measurement tools, smaller units of length, the coastline seems to get longer. The paradox challenges our understanding of real-world measurements and the concept of length, highlighting the infinite complexity of natural forms. Let's dive into the coastline paradox and explore how fractal geometry, infinite processes, and mathematical abstraction can transform our perception of real-world objects. The coastline paradox emerged from the work of Benoit B. Mandelbrot in the 1960s and 1970s, particularly in the field of fractal geometry. Mandelbrot, a French-American mathematician, discovered that many irregular complex shapes in nature, such as coastlines, clouds, and mountains, cannot be described by traditional Euclidean geometry. Instead, these shapes exhibit fractal properties, meaning they have intricate details at every scale. The paradox itself is tied to the fact that real-world objects, such as coastlines, have self-similarity at different scales. As you zoom in on the coastline, you notice more jagged edges and increased complexity. This means that measuring the length of the coastline is not straightforward. The more precisely you measure, the longer the coastline seems to be. The paradox was first observed when researchers tried to calculate the length of a coastline using a specific measurement technique. The result showed that, depending on the measuring scale, the unit of length used, the calculated length of the coastline, could vary. As the scale became smaller, the measured length grew without bound, illustrating the infinite complexity of the coastline's shape. The coastline paradox highlights a key feature of fractal geometry. Irregular shapes often have infinite detail when measured at smaller and smaller scales. It has profound implications in the study of natural shapes and geometric measurements, raising important questions about how we understand and quantify the world around us. The coastline paradox demonstrates the profound difference between Euclidean geometry the traditional geometry of shapes like lines, squares, and circles, and fractal geometry, which is used to describe irregular, jagged objects that appear in nature. This paradox, at its core, highlights the infinite complexity of natural objects and challenges our traditional notions of measurement. 1. The setup of the coastline paradox. The paradox begins with the simple idea of measuring the length of a coastline. A coastline is not a smooth, simple curve. It is highly irregular and jagged, with many small twists and turns. To understand the paradox, let's imagine trying to measure the length of a coastline with different sized rulers. If you use a large ruler, you may measure the distance along the coastline in a rough manner, ignoring all the tiny details and small twists in the land. If you use a smaller ruler, you will measure the coastline with more precision, and you will account for more small twists and turns in the coastline. This seems logical. The smaller the ruler, the more accurate your measurement should be. However, the paradox lies in the fact that as you keep making the ruler smaller and smaller, the length of the coastline seems to increase indefinitely. For example, let's say that with a large ruler you measure the coastline to be 100 miles long. When you switch to a smaller ruler, you might find that the coastline is 105 miles long, because the smaller ruler allows you to measure more of the jagged edges. If you keep reducing the ruler's size, the measured length will keep increasing, eventually becoming infinite. This result suggests that the coastline has infinite length in a finite space, which is paradoxical and counterintuitive. 2. The infinite detail of coastlines. To understand why this happens, we need to consider the idea of fractal geometry. In Euclidean geometry, the length of a curve is a well-defined number, and the shape of the curve can be described by simple equations or measurements. But coastlines are not simple curves. They are fractal-like, meaning they have self-similarity at every scale. As you zoom in on a coastline, you see more and more detail, and the coastline becomes more jagged. A key feature of fractals is that their detail increases infinitely as you zoom in. Coastlines are a real-world example of fractal objects because, at any level of magnification, the coastline looks similarly complex. This is different from a simple curve or line, which would become smooth and featureless as you zoomed in. As a result, when you measure a coastline with smaller and smaller rulers, you are essentially measuring an infinite number of increasingly smaller details that never settle into a finite number. 3. The concept of measuring the coastline. Now let's formalize the idea of measuring the coastline with different rulers. Suppose you want to measure the coastline using a ruler of length. Where is the unit of measurement? You would then start at one end of the coastline and use your ruler to measure how many times it can fit along the coastline's edges. With a large ruler, you measure the distance across only the most basic features of the coastline, ignoring the smaller twists. As you decrease the size of the ruler, you account for more of the smaller, finer features of the coastline, leading to a larger total measurement. Mathematically, this process can be thought of as a sum of lengths. The sum depends on the size of the ruler you use. In fact, the more precise the measurement, i.e., the smaller the ruler, the larger the calculated length becomes. The formula for calculating the length L of the coastline using a ruler of size depends on how the length of the coastline increases as the ruler gets smaller. The length increases because you are adding up all the smaller details of the coastline that were previously ignored when the ruler was larger. 4. The fractal dimension of the coastline. The key mathematical concept behind the coastline paradox is the idea of the fractal dimension of the coastline. A fractal dimension is a way to measure the complexity of a shape that is not smooth or regular. Unlike simple objects like squares or circles, fractal shapes don't have an integer dimension, like 1 for a line or 2 for a plane. Instead, they have a fractional dimension that reflects their complexity at every scale. The fractal dimension of a coastline can be calculated using the box counting method. This method involves covering the coastline with a series of boxes, or rulers, of different sizes, and counting how many boxes are needed to cover the entire shape. As the box size decreases, the number of boxes required to cover the coastline increases rapidly, indicating that the coastline has infinite detail. In fact, the fractal dimension of a coastline is typically greater than 1 but less than 2, meaning that the coastline is more complex than a simple line, but not as complex as a full 2D shape. This fractional dimension reflects the fact that the coastline exhibits infinite detail at every level of magnification. 5. The mathematical resolution. The problem of infinity, the coastline paradox, illustrates a key feature of fractal objects, their infinite complexity. As you zoom in on a fractal, you keep uncovering new details. Because the fractal dimension of coastlines is not an integer, the length of the coastline increases without bound as the scale of measurement becomes smaller. This is why measuring the length of a coastline is counterintuitive and paradoxical. While this might seem like a problem in measurement, it's important to remember that the infinite length of the coastline doesn't imply that the coastline physically has infinite size. Instead, it reflects the mathematical complexity of irregular shapes that exhibit self-similarity at every level of magnification. The paradox is a reminder that infinite detail is a feature of some natural objects, and our conventional methods of measurement don't always work in the infinite world of fractals. 6. Implications for geometry and physics. The coastline paradox has deep implications for our understanding of geometry and the physical world. Fractal geometry. The paradox shows the power and strangeness of fractal geometry. It highlights how irregular, jagged shapes like coastlines, mountains, and clouds have infinite complexity that cannot be captured by traditional geometric models. Measurement in the real world. In the real world, we understand that coastlines have a finite length that can be measured with reasonable accuracy. However, the paradox forces us to question how we define the length of natural objects when they exhibit fractal properties. Physics and scaling. The paradox has applications in scaling laws in physics. For example, energy dissipation and material properties can exhibit fractal behavior, where systems become more complex and less predictable at smaller scales. Understanding fractals can lead to insights in fields such as fluid dynamics, thermodynamics, and quantum mechanics. Coin rotation paradox. Imagine you have a coin lying flat on a table. Now pick up the coin and rotate it in place without sliding it. As the coin rotates, it traces a circular path around its own center. But here's the twist. If you roll the coin around the edge of another identical coin, a paradoxical situation arises. Despite the fact that you're rolling it around a circle, the coin doesn't flip. It rotates twice as much as you would expect. The result is that the coin ends up in an unexpected orientation. This seemingly simple motion of the coin leads to a strange paradox in geometry and physics, revealing surprising insights about how we think about rotation, motion, and infinite processes. The coin rotation paradox challenges our understanding of spatial relationships and rotation. Let's explore this paradox and uncover how infinite processes and rotational motion create results that seem impossible at first glance. The coin rotation paradox was introduced in the 19th century as part of the study of rotational motion and geometry. The paradox is rooted in the exploration of curved motion and the relationship between rotation and translation. It highlights an unexpected behavior when an object, such as a coin, is rolled around a similar object. The paradox was first recognized as part of the study of geometrical motion and transformation. It specifically illustrates how a rotating object doesn't behave in the way one might expect based on simple Euclidean geometry. The problem became a point of interest in mathematics and physics, particularly in the study of curved spaces and the mechanics of rolling motion. As this paradox suggests, spatial transformations, such as the movement of one object around another, can sometimes produce results that are not intuitive when we consider the object's rotation in space. The paradox challenges our basic assumptions about how rotation works and brings to light the non-intuitive effects of geometry and motion. Over time, this paradox has been explored in mathematics, mechanics, and philosophy, leading to insights into curved space and non-Euclidean geometry. The coin rotation paradox is part of a family of paradoxes that demonstrate the unexpected properties of geometrical motion and the fascinating outcomes of infinite transformations. The coin rotation paradox is a fascinating illustration of how motion, geometry, and infinite processes can lead to surprising and non-intuitive results. At its core, the paradox reveals a counterintuitive aspect of rotational motion and spatial relationships when an object is rolled around another identical object. Let's walk through the paradox and break down the concepts that make it so puzzling. 1. The basic setup. Rolling a coin around another coin. To begin understanding the coin rotation paradox, let's start with a simple scenario. Imagine you have two identical coins, each with a flat, circular shape. You place one coin stationary on a flat surface, and the other coin is placed on top. Now you roll the second coin around the edge of the first coin without slipping. At first, it seems like the second coin should rotate once as it rolls around the first coin's circumference. After all, as the coin rolls, it should rotate in place, and one complete revolution should match the distance traveled along the first coin's perimeter. But something strange happens. Instead of rotating once, the second coin actually completes 2 full rotations during its journey around the first coin. This outcome is what leads to the paradox. Let's examine the motion in more detail. The first coin remains stationary at the center. The second coin rolls round the edge of the first coin. 2. The expected outcome. 1 full rotation. If you consider the motion of the second coin as it rolls around the first, it's easy to think that the coin would rotate once for each complete lap. After all, if you were to roll the coin along a straight line, it would rotate once after covering a distance equal to its circumference. So, it seems logical that, as the second coin rolls along the edge of the first coin, it should complete 1 full rotation after covering the circumference of the first coin. The circumference of the first coin is c equals 2r, where r is the radius of the coin. As the second coin rolls around this distance, you might expect it to rotate once, because the rolling motion appears similar to unrolling the coin along a straight path. 3. The actual outcome. 2 full rotations. However, when the second coin rolls around, the first, it completes 2 full rotations instead of just 1. This is where the paradoxical aspect comes into play. To understand why this happens, we need to consider the relationship between rotational motion and the geometry of the path. The second coin is rotating due to both its own spin as it rolls, but also because of its motion around the circumference of the first coin. Each time the second coin completes a half turn, it covers the distance corresponding to half of the first coin's circumference. As the second coin rolls completely around the first coin's circumference, it undergoes 2 rotations, one from the rolling motion itself, and another because the point of contact between the 2 coins shifts as the second coin progresses around the edge. 4. Why 2 rotations? Understanding the mechanics. The key to understanding the coin rotation paradox lies in considering the combined effects of 2 motions. The coin's own rotation. As the second coin rolls, it rotates about its own center. This rotation happens as it moves along the edge of the first coin. The coin's motion around the first coin. The second coin also moves along a curved path, rotating as it moves around the first coin's edge. The second coin's total rotation is a combination of these 2 factors. Because the second coin is rolling around the edge of a circle, the point of contact between the 2 coins moves continuously around the perimeter of the first coin. This creates an additional rotational effect. In other words, the motion of rolling is compounded by the fact that the second coin is moving in a circular path, which leads to 2 full rotations instead of just 1. To clarify, think of it like this. The first coin's circumference creates a circular path that the second coin follows. As the second coin moves along this path, it rotates due to its own rolling motion. But because the path itself is curved, the second coin's spin becomes doubled, as the rotation from the motion along the circle adds an extra full turn to the overall motion. 5. The paradox. Why does this seem impossible? The paradox arises because we expect the coin to rotate once, based on our understanding of rolling motion. However, because the coin is rolling along a circular path, its rotation is affected by the geometry of the situation. The motion of the coin around the circle leads to a doubling effect on the number of rotations, which is counterintuitive. This paradox is similar to other geometric paradoxes where infinite processes or curved spaces lead to surprising results. The key issue is that, in circular motion, the relationship between rotation and distance traveled behaves differently than in linear motion. This difference results in an unexpected outcome. The second coin rotates twice instead of once. 6. The fractal and infinite implications. The coin rotation paradox is closely related to other paradoxes and infinite processes. In particular, it highlights the importance of curved spaces and geometrical transformations that are not immediately intuitive. Just as fractals display infinite complexity at every scale, the paradox shows how rotational motion around a curved path can lead to unexpected results. This paradox is often explored in discussions of rotational dynamics in physics, particularly when dealing with objects moving along curved surfaces or spatial transformations. The paradox challenges our traditional understanding of motion, rotation, and geometry, showing that simple actions like rolling a coin can lead to complex and counterintuitive results. 7. The real-world implications. While the coin rotation paradox is a mathematical and theoretical construct, it has implications for the real world, physics of motion. The paradox demonstrates how the geometry of curved paths affects rotational motion. Understanding this principle can help with the study of mechanical systems, such as wheels, gears, and rolling objects, engineering and design. The paradox has applications in fields like mechanical engineering, where understanding the behavior of rotating objects and curved paths is essential. For example, the gear systems in machines often involve rotational dynamics that resemble the situation described by the paradox. Mathematical physics. The paradox provides insight into the geometry of space and curved surfaces, which are important in general relativity and quantum mechanics. The non-Euclidean geometry of curved spaces is an essential part of modern physics. Gabriel's horn paradox. Imagine a horn, or a conical shape, that extends infinitely long but has a finite volume. Intrigued? Welcome to Gabriel's horn, a paradoxical shape that, while it seems impossible, exists mathematically. This shape has the peculiar property of having a finite volume but an infinite surface area. It's like a horn you could fill with liquid, but the surface would stretch on forever, making it impossible to cover entirely. The paradox raises questions about infinity, space, and measure, forcing us to rethink our intuitive understanding of geometry and the real world. How can something with an infinite surface have a finite volume? Gabriel's horn challenges our assumptions about volume and surface area, and forces us to confront the surprising and counterintuitive properties of infinite shapes. Let's explore the Gabriel's horn paradox and uncover the strange relationship between geometry, infinity, and mathematical abstraction. Gabriel's horn, also known as the Horn of Gabriel, is named after the biblical figure Gabriel, who is often associated with the concept of infinity in philosophical discussions. The paradox was first explored in the context of mathematical analysis in the 17th century, although it became better understood through the development of calculus in the 18th century. The paradox arises from the mathematical shape known as a surface of revolution. It is created by rotating the graph of a function, usually f(x) equals 1/x for x greater than equals 1, around the x-surface. The resulting surface extends infinitely, but the volume enclosed by the surface is finite. This result is part of the study of infinite series and limits. The shape itself was studied in mathematics by John Wallis and later by Gabriel Kramer, who formalized the relationship between infinite surface area and finite volume. The paradox has since been used to explore the nature of infinity and its role in geometry and calculus. Gabriel's horn paradox has since become a popular example in discussions of infinite objects in mathematics. It demonstrates how infinity can lead to counterintuitive results when applied to practical geometrical shapes and has become a staple in mathematical philosophy. The Gabriel's horn paradox presents a fascinating mathematical result where an object has an infinite surface area but a finite volume. The paradox revolves around the mathematical properties of a shape known as a surface of revolution, which is created by rotating a curve around an axis. In the case of Gabriel's horn, the curve used is f(x) equals 1/x, and the paradox arises from the interplay between infinite processes and finite outcomes. Let's break down the paradox and explore its implications. 1. The setup of Gabriel's horn. To construct Gabriel's horn, we start with the function f(x) equals 1/x for x greater than equals 1. This is a simple curve that starts at f(x1 equals 1 and decreases as x increases. As x approaches infinity, f(x(x) approaches 0, but never quite reaches it. This curve represents a hyperbolic decline, and it forms the basis of the shape we are interested in. Now, imagine that we rotate this curve around the x-axis. The result is a surface that starts at x equals 1 and extends infinitely to the right. The surface generated by this revolution is the mathematical shape known as Gabriel's horn. 2. The finite volume of Gabriel's horn. The first surprising property of Gabriel's horn is that despite the infinite length of the horn, the volume enclosed by the surface is finite. To understand why this is true, we need to calculate the volume of the object formed by rotating the curve around the x-axis. The formula for the volume of a solid of revolution is given by V equals abfx/2dx. In the case of Gabriel's horn, the function is fx squared equals 1/x, so we can calculate the volume as follows. V equals 1 to the power of 1/x 2dx equals 1 to the power of 1/x 2dx. This integral is relatively simple to evaluate. V equals double at the upper limit, x equals 1, the expression becomes 0, and at the lower limit x equals 1, the expression evaluates 2 minus 1. Therefore, the volume of Gabriel's horn is V equals 0.1 equals dot. Thus, the volume of Gabriel's horn is finite and equal to, despite the fact that the surface extends infinitely in the x direction. 3. The infinite surface area of Gabriel's horn. Now, let's consider the surface area of Gabriel's horn. The surface area of a solid of revolution is given by the formula A equals 2 abfx to 1 plus 4 plus 2x to x. For Gabriel's horn, we have fx equals 1/x, so we need to calculate the derivative of fx equals 1/x2. Substitute this into the surface area formula. A equals 21 to the power of 1/x, 1 plus 1/x4x2. This integral doesn't have a simple closed-form solution, but it's clear that the integral diverges. As x approaches infinity, the expression 1 plus 1/x4 approaches 1, and the integral behaves similarly to the integral of 1/x over an infinite range. The integral of 1/x from 1 to infinity is known to diverge, meaning that the surface area grows without bound. Thus, the surface area of Gabriel's horn is infinite, even though the volume is finite. 4. The paradox. Infinite surface area, finite volume. The Gabriel's horn paradox arises because of the surprising result that the volume of the horn is finite, but the surface area is infinite. This paradoxical outcome seems impossible in the real world, where an object with infinite surface area would typically be thought to have an infinite volume as well. However, the paradox highlights a key feature of infinite processes in mathematics, that some objects can have finite volume but still have infinite surface area. This result challenges our intuition about space and geometry. In practical terms, the paradox demonstrates that infinity behaves very differently when applied to mathematical objects compared to how we experience it in the physical world. The surface of Gabriel's horn stretches on forever, while the amount of material required to fill the horn is finite. 5. Resolving the paradox. Understanding infinity in geometry. To resolve the paradox, we must recognize that Gabriel's horn exists in the realm of mathematical abstraction and idealized objects. In the physical world, it would be impossible to create a real object with infinite surface area and finite volume because of physical constraints like materials and space. The paradox exists only in the world of mathematics, where we deal with idealized objects that have properties governed by the rules of infinite processes. In real-world physics, there are no true infinite objects. The paradox serves as a reminder that mathematical abstractions can lead to surprising results that defy physical intuition, but these results are valid in the context of mathematical models and idealized spaces. 6. Physical and mathematical implications. The Gabriel's horn paradox has several implications for both mathematics and philosophy. Mathematical abstraction. The paradox challenges our intuition about infinite objects. It shows that infinity can lead to counterintuitive results in geometry, where objects can have finite volume but infinite surface area. This has implications for how we think about infinite processes and infinite series in mathematical models. Measure theory. Gabriel's horn also highlights the distinction between volume and surface area in the context of measure theory. The paradox demonstrates how an object can have a finite volume but an infinite surface area, emphasizing the importance of carefully defining and understanding measures in different contexts. Physical reality. The paradox raises questions about how mathematical models can be applied to the physical world. While Gabriel's horn is a theoretical construct, it serves as a reminder of the limits of mathematical abstraction when trying to apply it to real-world objects. Hausdorff paradox. Imagine trying to create a set of points in three-dimensional space, where you can divide it in such a way that, in the end, you have two identical copies of the original object despite only having used one finite object. The Hausdorff paradox presents a seemingly impossible situation where an object, despite being split into pieces, is reassembled into two perfect copies of itself. It's as though the mathematical magic of infinite sets allows the duplication of an object without violating any physical laws. This paradox highlights the strange behavior of sets and measure theory when dealing with infinite objects. The Hausdorff paradox not only challenges our understanding of space, measure, and geometry, but also shows how mathematical abstraction can lead to surprising and seemingly contradictory results. Let's dive into this paradox and explore how infinite sets and group actions create a situation where we can form two identical copies from a single set, all governed by the axiom of choice. The Hausdorff paradox is named after the German mathematician Felix Hausdorff, who is known for his work in topology, set theory, and the study of measure theory. The paradox was first introduced in 1914 as part of Hausdorff's work in mathematical analysis and the exploration of infinite sets. The paradox involves splitting a set into a finite number of parts and then reassembling the pieces in such a way that two identical copies of the original set are created. Hausdorff showed that this can be done in the context of a three-dimensional object, like a ball, by using the axiom of choice, a powerful principle in set theory that allows for the selection of elements from infinite sets in ways that are often counterintuitive and difficult to visualize. Hausdorff's work built on the foundations of measure theory, which deals with assigning values like length, area, or volume to sets. The paradox challenges our basic understanding of volume and measure in spaces where infinite sets and mathematical abstractions play a key role. The Hausdorff paradox is a famous example of how infinite sets and group actions can create geometrical results that seem impossible in the real world. The paradox has since been widely studied in mathematics and philosophy, particularly in the field of mathematical logic and the philosophy of infinity. It serves as a thought-provoking example of how infinity and abstract mathematics can lead to results that defy our physical intuition. The Hausdorff paradox reveals the bizarre behavior of infinite sets when subjected to certain group actions and mathematical transformations. At its core, the paradox shows that an object, like a ball in three-dimensional space, can be divided into a finite number of pieces and then reassembled into two identical copies of the original object. This seemingly impossible feat is made possible by the axiom of choice and the properties of infinite sets. 1. The setup of Hausdorff's paradox. The paradox begins with the axiom of choice, a foundational principle in set theory that allows for the selection of elements from an infinite set without specifying how to make the selections. This axiom enables us to create non-measurable sets and manipulate them in ways that defy intuition. The Hausdorff paradox involves the following steps. Start with a three-dimensional object, like a solid ball or sphere. Divide the object into a finite number of pieces. The key is that these pieces will be mathematically defined and may not have a traditional geometric interpretation. Reassemble the pieces in such a way that you end up with two identical copies of the original object. At first glance, this seems impossible. How can you split a finite object into pieces and end up with two identical objects? The answer lies in the use of infinite sets and the axiom of choice. 2. The role of the axiom of choice. The axiom of choice is a key principle in set theory, and it plays a crucial role in the Hausdorff paradox. The axiom states that for any collection of non-empty sets, it's possible to choose one element from each set, even if there's no explicit rule for making the selections. This ability to make choices from infinite sets leads to results that seem paradoxical or counterintuitive when applied to real-world objects. In Hausdorff's construction, the axiom of choice is used to divide a three-dimensional object, like a sphere, into pieces. These pieces are not like the typical geometric shapes we encounter in everyday life. Instead, they are abstract and non-measurable sets that cannot be visualized in the traditional sense. Because of the axiom of choice, these non-measurable sets can be reassembled in a way that creates two identical copies of the original object. This result is a direct consequence of the infinite nature of the pieces and the ability to manipulate them through group actions. 3. The group actions and reassembly process. The next step in the paradox involves using group actions to reassemble the pieces. Group actions are mathematical operations that allow us to transform a set in a way that preserves certain properties. In the case of Hausdorff's paradox, we use rotations and translations to manipulate the pieces of the original object. Here's how the object into a finite number of pieces, using the axiom of choice, apply a series of rotations and translations to these pieces, essentially moving them in space without distorting them. Reassemble the pieces in such a way that the result is two identical copies of the original object. The critical idea here is that because the pieces are non-measurable and abstract, their reassembly can create two copies of the original object, even though the process appears to be mathematically impossible. 4. Non-measurable sets and the paradox. The most puzzling aspect of the Hausdorff paradox is the concept of non-measurable sets. In classical geometry, objects have a well-defined volume or measure, and when you divide an object into pieces, you can calculate the volume of the pieces and the total volume of the object. However, in the case of Hausdorff's paradox, the pieces that are created by the axiom of choice do not have a well-defined volume in the usual sense. They are non-measurable, meaning that they don't conform to traditional ideas of size or geometry. This property of non-measurability is crucial to the paradox because it allows for the rearrangement of the pieces into two identical objects. Without the axiom of choice and the ability to create non-measurable sets, the paradox would not be possible. 5. The paradox of duplication. The core of the paradox is that you can duplicate an object, despite the fact that it only had one set of pieces to begin with. This raises several questions about the nature of space and measure, space and geometry. How can you divide an object into pieces and then reassemble it into two identical copies? The paradox shows that the rules of geometry can behave differently when dealing with infinite sets. Volume and measure. The paradox challenges our understanding of volume and measure. How can an object with one volume be split into pieces and turned into two objects with the same volume as the original? Infinity. The Hausdorff paradox forces us to confront the strange and often unintuitive properties of infinity. It reveals that infinite sets can be manipulated in ways that are not possible in the finite world. 6. Implications of the Hausdorff paradox. The Hausdorff paradox has profound implications for both mathematics and philosophy. Mathematical abstraction. The paradox highlights the power and strangeness of mathematical abstraction. It shows how infinite sets can create situations that defy physical intuition and challenge our understanding of space and geometry. Measure theory and non-measurability. The paradox underscores the importance of measure theory and the concept of non-measurable sets in set theory. It also shows how traditional ideas of size and measure break down when dealing with infinite objects. Philosophical implications. The paradox raises deep questions about the nature of reality and the limits of mathematical models. Can infinite sets really be used to explain the real world, or do they only work within the realm of mathematical abstraction? Physical reality. While the paradox is a mathematical construct, it reminds us that infinite objects don't exist in the physical world. The paradox serves as a thought experiment that forces us to reconsider our understanding of space and infinity in the real world. Hooper's paradox. Imagine you are faced with a decision where you must choose between two options, but there's a catch. One of the options is designed to trick you. You are given a set of probabilities and some background information about the choices, but as you dig deeper into the situation, you realize that the probabilities contradict the inference you made about your best course of action. The more you analyze, the more your expectations seem to crumble. Each option leads to a surprising outcome that defies your reasoning. This is the essence of Hooper's paradox, a problem that challenges the way we make probabilistic decisions and understand inference. The paradox forces us to reconsider our basic assumptions about how we infer the likelihood of events and how probability interacts with our decision-making processes. Let's explore Hooper's paradox and uncover why probabilities, decisions, and inference don't always behave in ways we expect. Hooper's paradox was introduced by the American philosopher and mathematician James Hooper in 1979. The paradox focuses on the relationship between decision-making, probability theory, and inference. It emerged from Hooper's work on decision theory, which seeks to model rational decision-making in uncertain environments. The paradox arises from a situation in which a person is presented with two choices, both of which are associated with certain probabilities. However, as the person works through the problem and uses Bayesian inference, the process of updating beliefs based on new evidence, they find that the logical conclusion they reach about the best course of action is contradicted by the actual probability. This creates a scenario in which intuitive reasoning seems to break down, leading to an unexpected and paradoxical outcome. While the paradox itself is often framed as a thought experiment in probabilistic decision theory, it has broader implications for how humans make decisions under uncertainty. It forces us to think more critically about how we handle incomplete information, update our beliefs, and make rational choices based on probabilistic evidence. Hooper's paradox continues to be studied as part of the field of philosophical decision theory and probability. The Hooper's paradox is a thought experiment in decision theory that explores the counterintuitive results of applying probability theory and Bayesian inference to real-world decisions. At its core, it reveals the surprising effects of seemingly contradictory evidence and how our intuitions about probabilistic decisions can be fooled by unexpected patterns of reasoning. 1. The setup of Hooper's paradox. Let's start by presenting a basic setup for Hooper's paradox. In this paradox, you are presented with two options and asked to choose between them. Option A. You are given a choice to invest in a project that has a 40% probability of success, and you are informed that if the project succeeds, it will provide a large reward. Option B. Alternatively, you are offered a project with a 60% probability of success, but the rewards are much smaller if it succeeds. On the surface, you might logically think that option B is the better choice, since it has a higher probability of success, 60% versus 40%, and seems to provide a better chance of an outcome in your favor. But here is where the paradox takes shape. When you apply Bayesian inference and update your beliefs based on additional information or evidence about the options, the situation begins to unravel. 2. Applying Bayesian inference to the decision. Bayesian inference is a method of updating probabilities based on new evidence. In the context of Hooper's paradox, you are updating your beliefs as you receive more information about the potential outcomes of the two options. Let's say that, after looking at new data or considering a history of similar choices, you update your beliefs about the two options. Option A, with a 40% chance of success, turns out to have a very high risk of failure and a significant downside if it fails, while option B, the 60% chance, turns out to be more stable with a better expected value, even though its immediate success rate is higher. As you process this new information, Bayesian updating suggests that the actual expected value, a combination of probabilities and rewards, of option A might now seem worse than option B, despite the higher success rate of option B. 3. The paradox. Intuitive decision-making breaks down. The paradox happens because, despite your initial preference for option B due to its higher probability of success, the updated expected value suggests that option A is actually better in the long run, given the additional context provided by the Bayesian reasoning. This paradoxical result can feel illogical or counterintuitive. You initially believed that probability alone should drive your decision-making. However, once you consider other factors or update your belief with Bayesian inference, the results force you to reconsider the apparent advantage of option B. Thus, the paradox reveals the limitations of simple probabilistic reasoning when new evidence changes the dynamics of the situation. Hooper's paradox forces us to confront the idea that our decision-making process, when it depends solely on raw probabilities, might be missing key contextual factors that shift the balance between our choices. 4. Probability versus expected value. The role of context. The fundamental idea behind Hooper's paradox is the tension between probability and expected value. Probability measures the likelihood of an outcome occurring. Expected value incorporates both the probability of an outcome and its associated reward. While option B has a higher probability of success, it might have a much lower reward when it does succeed. On the other hand, option A might be a riskier choice with a lower probability of success, but the reward for success is so high that its expected value actually exceeds that of option B. This introduces a fundamental issue. Probabilistic reasoning alone doesn't always account for the value of outcomes, i.e. the reward or loss. In Hooper's paradox, the initial choice you make, based on probabilities, might be overridden by the true expected value, which incorporates both probability and reward. 5. The counterintuitive outcome. How can this be? So, why does this happen? Why does expected value differ from probability in a way that leads to a counterintuitive decision? The issue arises because human intuition often relies on simplified reasoning, probabilities alone, to make decisions, while the more sophisticated approach, such as Bayesian inference, requires a deeper understanding of context and expected outcomes. Hooper's paradox forces us to reckon with the fact that probabilistic decisions can be misleading if we fail to incorporate the full picture of rewards, risks, and updated information. In the paradox, you would be justified in choosing option B based on probabilities, but Bayesian reasoning ultimately tells you that option A may lead to a better long-term outcome, even though it initially seems like a riskier choice. 6. Resolving the paradox. Embracing complexity in decision-making. To resolve the paradox, we need to recognize the importance of context and expected value in decision-making. The paradox reveals that probability alone is insufficient to make complex decisions, especially when we are dealing with uncertainty and incomplete information. Bayesian inference allows us to update our beliefs about future outcomes based on new evidence. Expected value helps us make more comprehensive decisions by considering both the likelihood of success and the reward for success. Ultimately, Hooper's paradox highlights the limitations of intuition when it comes to decision-making under uncertainty. It encourages us to take a more systematic approach to decision theory, where we update our beliefs and consider all available information, rather than relying solely on initial probabilistic estimates. 7. Philosophical and mathematical implications. Hooper's paradox has significant implications for both mathematics and philosophy, decision theory. The paradox demonstrates the importance of expected value in decision-making and the shortcomings of simple probabilistic reasoning. It suggests that human intuition about probability may often be incomplete or misleading when it comes to making real-world decisions. Philosophy of probability. The paradox raises questions about the nature of probability and inference. Can probability alone drive decision-making, or do we need to consider the full context of the situation? The paradox pushes us to consider the role of subjective beliefs, uncertainty, and expected rewards in our decisions, rationality and choice. Hooper's paradox also forces us to reconsider what it means to be a rational decision-maker. If our intuitive decisions lead to paradoxical outcomes, what does this say about rationality and the logical consistency of our choices? Nicodem set paradox. Imagine a situation where you have a set of elements that seems to behave paradoxically. You may think you understand the size or measure of a set, but what if the measure can change based on how the set is constructed? Enter the Nicodem set paradox, a fascinating mathematical paradox that delves into the concepts of measure theory, infinite sets, and probability. In the Nicodem paradox, we encounter a set that, while appearing to have a well-defined measure, leads to a situation where it behaves in a way that defies typical rules of set construction. This paradox forces us to confront deep questions about the nature of measure and how we assess size in the world of infinite sets. Can a set appear to have a finite measure, yet behave in a way that makes it appear infinitely large? Let's explore the Nicodem set paradox and see how infinite sets challenge our conventional understanding of measure theory and probability. The Nicodem set paradox was introduced by the Polish mathematician Oskar Nicodem in the 1930s as part of his research in measure theory and set theory. Nicodem was primarily concerned with the mathematical foundations of measure theory, which deals with the assignment of sizes to set, especially when those sets are infinite or highly irregular. The paradox involves a particular type of set that, while having a well-defined measure or size, can still lead to paradoxical behavior when we attempt to partition it or apply certain operations to it. This paradox highlights the difficulty of dealing with infinite sets and measure theory when the sets in question are non-measurable or irregular in nature. Nicodem's work on this paradox built on the theories of Lebesgue measure and the axiom of choice, which are central concepts in set theory. The paradox demonstrates how sets, especially those with non-trivial properties, can behave in ways that challenge our intuition about size, measure, and probability. The Nicodem set paradox has important implications for mathematical logic, probability theory, and the philosophy of mathematics, as it forces us to reconsider the conventional methods of assessing the measure of sets, particularly in the context of infinite collections. The Nicodemus set paradox is a result of measure theory, set theory, and infinite sets that challenges our understanding of size and measure. The paradox arises when certain sets, despite having a well-defined measure, exhibit behavior that leads to unexpected or counterintuitive results. This paradox is an important contribution to the study of non-measurable sets and infinite sets, forcing mathematicians and philosophers to rethink how we approach size, measure, and probability in infinite contexts. 1. The setup of the Nicodemus set paradox. The paradox begins with the concept of measure in mathematics, which deals with assigning a size or volume to objects, such as lines, surfaces, and higher dimensional sets. In Euclidean geometry, we have an intuitive sense of measure. The length of a line, the area of a surface, or the volume of a three-dimensional object can be easily understood and calculated. However, when we move into the world of infinite sets, things become less intuitive. The Nicodemus set is a set that appears to have a finite measure, but behaves paradoxically when we attempt to manipulate it using traditional set-theoretic operation. In this paradox, we deal with a set that is defined in terms of probability, and its measure is treated according to Lebesgue measure, the standard way of assigning size to sets in real analysis. To understand the paradox, imagine a set S that is defined on the real number line. The set S might appear to be a typical interval or a collection of intervals that we would expect to have a well-defined length or measure. However, when we manipulate the set in certain ways, such as by partitioning or rearranging it, the resulting set may behave in a way that defies intuition about its size or measure. 2. The paradox of non-measurable sets. The Nicodemus set paradox arises from the study of non-measurable sets, sets whose measure cannot be defined in the usual way. Non-measurable sets are often constructed in real analysis using the axiom of choice, which allows us to select elements from infinite sets in ways that seem counterintuitive. In the case of the Nicodemus set, we begin with a set that appears to be measurable, but, due to the properties of infinite sets, leads to paradoxical conclusions when we try to apply measure theory to it. For example, when we attempt to partition the set into smaller pieces, we may find that the sum of the measures of the parts does not equal the measure of the whole set, even though all parts are taken from the original set. This creates a contradiction. We started with a set that seemed to have a well-defined size, but after applying certain operations, we find that the measure is not well-behaved or consistent. This paradoxical result challenges our intuitive understanding of measure and infinity, and it forces us to reconsider how we define the size of a set in a mathematically rigorous way. 3. The paradox of partitioning and reassembling sets. One of the central ideas in the Nicodemus set paradox is the partitioning and reassembling of sets. In traditional geometry, if you divide an object into smaller pieces and then reassemble them, the resulting object should have the same size or measure as the original. However, in the context of infinite sets, this assumption breaks down. Consider the following. We begin with a set that has a finite measure. We divide the set into smaller parts, using a process that respects the measure theory. After reassembling the parts, the resulting set may have an unexpected size or measure, leading to a paradoxical result. For example, you could divide a set into non-measurable pieces using the axiom of choice and then reassemble those pieces. When this happens, the resulting set may have a size or measure that contradicts what we expect based on the original set. This illustrates the paradoxical nature of infinite sets and highlights the limits of applying traditional measure theory to with infinite components. 4. The role of probability and inference. The Nicodemus set paradox also involves probability theory, as it can be viewed as a probabilistic paradox. The set in question is often constructed in the context of probability spaces, where sets represent outcomes in a probabilistic model. The paradox arises when the measure of these sets behaves in ways that don't align with probabilistic expectations. The probability space is typically defined as a set of outcomes, with each outcome having a specific probability. The measure of a set within the probability space corresponds to the probability of the outcomes that belong to the set. In the case of the Nicodemus set, we encounter a situation where the measure or probability of a set doesn't behave predictably when we partition or rearrange the set. This leads to a contradiction in our expectations about how probability and measure should behave. 5. The paradox's implications for measure theory and set theory. The Nicodim set paradox has profound implications for both measure theory and set theory. Measure theory, the paradox challenges our understanding of measure, especially in the context of infinite sets. It shows that measure theory doesn't always provide a consistent or intuitive way to handle non-measurable sets, especially when infinite sets are involved. Set theory and the axiom of choice. The paradox relies on the axiom of choice, which allows for the construction of non-measurable sets. The axiom of choice is a powerful tool in set theory, but it also leads to results that seem counterintuitive or paradoxical, as in the case of the Nicodim set, probability theory. In the context of probability, the paradox highlights the limits of probabilistic reasoning when dealing with infinite sets and non-measurable events. It forces us to reconsider how we apply probability theory to infinite outcomes. 6. Resolving the paradox. Understanding non-measurable sets. The resolution of the Nicodim set paradox lies in the recognition that non-measurable sets behave differently from measurable sets. In particular, the paradox illustrates the limits of traditional geometry and measure theory when applied to infinite sets. By understanding the axiom of choice and the concept of non-measurable sets, we can appreciate why sets like the Nicodim set exhibit behavior that contradicts our physical intuitions about size and measure. In mathematical terms, the paradox shows that infinite sets do not always conform to the usual rules of measure theory, and that partitioning and reassembling sets can yield unexpected results. Sphere inversion paradox. Imagine taking a solid sphere and trying to turn it inside out, like flipping a glove. Now, here's the catch. You're not allowed to rip or cut the sphere. You must perform the entire transformation through continuous deformation, stretching and bending the sphere without creating any holes or breaks. It seems impossible, right? But in the world of topology, a field of mathematics concerned with properties that remain unchanged under continuous transformations, the sphere inversion paradox shows that this feat is mathematically possible. Though it's a paradox in the sense that our physical intuitions about space and geometry fail to capture how this can happen. The sphere inversion involves transforming a sphere into its mirror image without any cuts or tears. This seemingly impossible process is a surprising outcome of topological principles and offers a counterintuitive glimpse into the world of continuous transformations. Let's explore the sphere inversion paradox and discover how topological deformation challenges our assumptions about shape and space. The concept of sphere inversion first gained significant attention in mathematics through the work of mathematician Stephen Smale in the 1950s. Smale's work in topology demonstrated that it was mathematically possible to invert a sphere, turn it inside out, using continuous deformation. But this transformation was not intuitive and seemed impossible to imagine in physical space. Smale's result was groundbreaking, as it showed that despite our geometric intuitions suggesting that such a transformation was impossible, it could be done without tearing, gluing, or cutting the sphere. The result was later formalized and visualized with the development of computer simulations and animation that demonstrated the process of sphere inversion step by step. Smale was awarded the Fields Medal in 1966, partly for his work on sphere inversion, which revolutionized the way mathematicians and physicists thought about topology and continuous deformation. The paradox itself was not only a fascinating mathematical problem, but also an example of the counterintuitive nature of topology, where continuous transformations can lead to unexpected results. Since then, the sphere inversion paradox has become a celebrated example in mathematics and topology, often shown in educational contexts and mathematical demonstrations. It continues to inspire thought in fields ranging from geometry to mathematical philosophy, showcasing the surprising power of topology in understanding space and shape. The sphere inversion paradox is a remarkable mathematical phenomenon that arises from the principles of topology and the concept of continuous deformation. The paradox illustrates that, despite appearing impossible from a geometrical perspective, it is in fact possible to invert a sphere, turn it inside out, using a continuous, smooth transformation, without cutting, tearing, or gluing. Let's break down the paradox step by step to understand the principles behind this fascinating result. 1. The setup of the sphere inversion paradox. The basic idea behind sphere inversion is simple. We begin with a standard sphere, such as a rubber ball, and attempt to invert it. That is, we try to make the inside of the sphere become the outside and vice versa, all without tearing or cutting the sphere. In our physical intuition, this seems impossible, because the sphere has a well-defined surface, and flipping it inside out would require breaking the continuity of the surface. However, in topology, the situation is very different. Topological spaces are concerned with the properties that are preserved under continuous deformations, such as stretching, bending, and twisting. As long as we don't tear or glue the surface, we are allowed to deform the sphere continuously. The key idea of the paradox is that although we cannot simply flip a sphere in the same way we would flip a pancake, the sphere can still be turned inside out through a continuous deformation that stretches, twists, and bends the surface in a way that we might find hard to visualize, but that is topologically valid. 2. The mathematical foundation. Topology and continuous deformation. The key to the sphere eversion paradox lies in the field of topology, which studies properties of objects that are preserved under continuous deformation. In topology, objects that can be continuously transformed into each other are said to be topologically equivalent. For instance, a circle can be continuously deformed into a square without tearing or gluing, even though they may appear geometrically different. Similarly, a sphere can be continuously transformed into an inverted sphere without violating the rules of topological equivalence. The transformation from a regular sphere to its inverted counterpart is not a simple flip. Rather, it involves a series of steps that gradually twist and deform the sphere. At various points in the transformation, the sphere may appear to collapse or form unusual shapes, but because these are all continuous deformations, the transformation is still mathematically valid. 3. The process of sphere eversion. To fully understand sphere eversion, we need to consider the actual steps involved in the transformation. The process of eversion can be thought of as a sequence of stages in which the sphere gradually changes from its original state to the inverted one. At each stage, the sphere is deformed continuously, but never broken or torn. Let's break down the general steps of eversion. Initial stage, the sphere starts as a regular, undistorted shape. In the first stage, the sphere begins to distort by flattening in places, creating new creases and bending the surface, but the sphere remains topologically intact. Intermediate stage. As the deformation progresses, the sphere flattens and stretches more, causing regions of the sphere to become closer together. However, at this stage, the sphere is still not yet flipped. It's just going through a series of distortions. Critical point. There is a point in the process where the sphere starts to look like a flattened pair of pants, with the inside of the sphere beginning to be exposed. This stage requires careful manipulation of the sphere's surface to ensure that the transformation remains continuous and does not break. Inversion. At the final stages of eversion, the sphere reverses, with the inside and outside swapping places. This inversion happens gradually, with the shape twisting and morphing, but never being torn apart. In the end, the sphere is turned inside out, and we have two identical spheres, one in its original state and one in its inverted form. 4. The topological nature of the paradox. What makes the sphere eversion paradox so surprising is that it defies our geometrical intuition. In Euclidean geometry, objects are often defined by precise shapes and distances. A sphere, in this sense, is a perfectly round object, and flipping it would seem to require a sudden drastic change in shape. However, topologically, the surface of the sphere is treated more abstractly. It's the continuity of the surface that matters, not the exact geometry. In topological terms, a sphere is a simple object that can be deformed continuously into many different shapes, as long as the surface doesn't experience any discontinuities, no tearing, no cutting. This is what allows us to invert the sphere, even though we might have trouble imagining how it could be done without breaking the object apart. The idea that we can continuously deform the sphere from one state to another is a core principle of topology, and it highlights the distinction between geometrical and topological properties. While geometry deals with shapes and sizes, topology is concerned with the connectivity and continuity of objects, which opens up possibilities for transformations that are impossible in the world of Euclidean geometry. 5. The paradoxical nature of eversion. The paradox in sphere eversion arises from the fact that physically, it seems impossible to invert a solid sphere without cutting, tearing, or distorting it in ways that would make it impossible to reassemble. However, in the mathematical world of topology, the concept of continuous deformation allows for such a transformation to take place. Geometrical intuition. In the world of everyday objects, our intuition tells us that flipping a sphere inside out would be an impossible task. The sphere's smooth, continuous surface suggests that there's no way to invert it without cutting or distorting the shape. Topological intuition. In the world of topology, however, the surface of the sphere is treated differently. As long as the continuity of the surface is maintained and no tearing or gluing occurs, the eversion is possible. The paradox is not a contradiction in the rules of mathematics, but rather a demonstration of the power of topology to redefine how we think about shapes and transformations. It challenges the assumptions that we take for granted about the world around us, showing that mathematical abstraction can lead to results that are radically different from our physical experiences. 6. Real-world implications and applications. While the sphere eversion paradox is primarily a mathematical curiosity, it has broader implications in several fields. Mathematical visualization. The paradox is used to demonstrate the power of visualization in understanding complex mathematical concepts. Computer simulations and animations of sphere eversion help students and researchers understand the implications of topological transformations. Differential geometry and physics, the ideas behind sphere eversion, also have applications in differential geometry, particularly in the study of curved spaces and the deformation of shapes. These concepts play a role in general relativity, where the curvature of space-time can involve continuous transformations. Robotics and engineering. Understanding continuous transformations is crucial in robotics and engineering, where parts of machines might need to undergo smooth, continuous deformations as they interact with each other or the environment. The concept of sphere eversion can help in optimizing mechanical processes that involve smooth, continuous transitions